Sure, correct. I just started stream on YouTube.
Can someone just tell me if the screen sharing is fine, if you see the slides?
Yes, it's fine.
Okay, excellent.
I see it.
Can I also check my presentation?
Yes, of course. Go ahead. Yes, I see your screen, but it is not full screen, I think.
Yes, I'm trying to make it. Okay.
Oh, yes, now it's fine.
Okay, fine. Thanks.
You're welcome.
Okay.
Hi, hello. Can you hear me?
Yes, hello.
Yeah, I cannot see the breakout rooms.
Okay.
Is it already open, or
Are
is
you
it a problem
using,
that I have?
are you using standalone application or web browser?
I have Zoom downloaded in my machine, but I don't see the room.
So
breakout
maybe you
rooms.
have too old version. Your version is too old.
Okay, so I should try to update my Zoom and then try again then.
You can. If not, you can always use web browser. There's always the newest version there.
Okay. Okay, so I'm gonna log out and log in again with the new version.
Okay.
Thank
Yeah.
you.
Hello,
Rafał left us, I think.
and what about Piotr Salabura?
I haven't seen him today.
Sorry, but this is the address we are going to meet for this opening, right?
Also, yes, but now we have a technical session just for checking software and
But
so
the
on.
same address will be used for opening,
Yes,
right?
correct. Yeah.
Okay. Cześć, Piotr.
Can I also quickly check my screen sharing?
Yes, of course.
Okay, let me try. Okay. This seems to work, right?
Yes, I see it.
Very good.
Very good. Yes.
Thanks a lot.
That's all.
היי אלי. אני משוחח עם אלי פרידמן דרך קרקוב.
בוקר טוב, אברהם.
אני לא שומע אותך. לא פתחתי את הווליום אצלי, חכה. הספיקר אצלי לא פתוח, עכשיו אתה שומע אותי? אני
שומע אותך, אתה שומע אותי?
כן, מצוין, כן. אוקיי, בדקתי ציוד. אתה מתכונן לשמוע הרצאות היום?
רק את הפתיחה חשבתי.
כן. אני אולי אפילו את זה לא, אבל רשמתי לי הרצאות ליום רביעי, שיש לא מעט בתחום שלנו.
כן, רשמתי 4.
כן. כן, בערך, כן, 1, 2, 3, 4, כן.
טוב, אנחנו כעת מפריעים לכולם, אז בואו נסגור.
אוקיי, להתראות.
Hello, everyone. Is it possible to test my setup?
Yes, sure. Hi.
Go on.
Hello. So it seems that you hear me and
Yes.
video is working as well. I try share screen just for quickly if I can. So.
Oh yes. We mean
okay.
any equations.
Yeah. And it's full screen. Okay. So it seems that it's working. I have to stop sharing over. How can I do this? Pop. Where is that? Now I cannot go back to the.
I can do it for you.
Where can I find that? Stop share. I can.
Stop sharing, yes.
Okay. Okay. Nice. Yeah. Okay. Thank you. Thank you very much.
Mhm.
See you. Bye.
Cześć Damian, słyszysz mnie?
Dobrze i wyraźnie. Cześć.
No to okej. Czyli w takim samym trybie rozumiem, jak tam będzie moja pora PowerPointa screen sharing zrobić
Zgadza się.
i to w ten sposób leci.
Puścimy ci zegar, żebyś wiedział, ile masz
No
czasu.
właśnie, to wiesz,
Tak,
specjalnie.
jestem już tak uczulony na ten czas, że cały czas ćwiczę tutaj i kondensuję moje zdania.
Byleś nie skondensował tak, że się nikt z tego nie domyśli, o co chodzi.
No, więc tutaj taką złoty środek próbuję właśnie, szlifuję.
Jak zwykle w ostatniej chwili.
No, jeszcze parę godzin jest.
No właśnie, jeszcze parę godzin. No nie. Dobra, to jak mnie słychać, to dobrze. To
Tak jest.
dzięki.
Cześć, Olu.
Dzień dobry, Damianie. Hello, everyone, actually. Good to see at least the names, if not the faces, then the names of some friends.
Well, you can see also my face, yes. Jim is also, hello, hi.
Hi, Jim.
Good to see you.
Very good. So, anything I need to know as a chairperson for the afternoon? Hello, Abraham.
You need to know the timetable.
This I am prepared. I'm talking about technicalities.
I don't.
Okay, good.
Damian will take care with Rafał about technicalities, I hope.
Perfect. But that was really unfortunate with the COVID pandemic and with the new team that took over the organization of MESON. It was double difficulty.
Yeah, but
Many
everything
people.
will be unimportant if this all COVID things would be removed soon. I mean, that is all small details which we had to face here.
So in which room is there this broadcast of the Market Square?
In a breakout room, if you go there,
My
main square, yeah.
there is a main square.
Okay.
But I mean, these people which are in there, this is, I mean, this is not, this is the current status, this is green, right? The people which are currently in these other rooms, and the people which were there were indicated by gray, right? Is it correct?
Yes, green dot, yes, correct.
Okay, so then to everybody who are connected, you can enjoy the view from Main Square and Wawel Castle, waiting still for opening of a conference. This is a small substitute of not being in person in Krakow.
Cześć koledzy.
Dzień dobry.
Dzień dobry.
Słychać dobrze i wyraźnie.
Słychać, tak?
Tak.
Dobrze.
Czy to
Właśnie.
profesor Szczurek się odzywa?
Witam panią profesor.
No właśnie się zastanawiałam, czy tylko
Rączki
kolegów, czy
rączki-
koleżanki również pan
Rączki
profesor
całuję.
wita.
Rączki całuję.
Dzień dobry.
Cześć, cześć. My zaczynamy 11:45, ja dobrze to pamiętam, czy 12?
11:45, tak.
Tak, nie, bo to jakoś już się zgubiłem w tych...
12:00 musicie skończyć.
Nie, to skończymy, nie będziemy dobrze gadać.
Hello, everyone. I have one quick question, whether the opening and plenary session will be held here in the main room
Yes,
or
correct.
somewhere else? Okay, thank you.
Welcome.
Ja też jestem podobny. Nie, gadam spotkanie z tą zaczynamy mecz. Dobrze. Na razie.
Hello.
Hi.
Hi.
Hello.
Do you see my screen?
Yes, we can see.
This is this some excitation functions or something like that.
Yes, but it's not in full screen mode. It's in edition mode.
Okay. You such a way.
Yes, it's better. It's bigger.
Okay. Okay. Good. Thanks a lot. I only wanted to try out.
Yeah, sure.
Okay. Thanks.
Welcome.
So yeah, hello, good morning, or
Good morning.
together. Yeah, obviously my microphone works, so I want to check that. Okay.
I think it's time to start. Yeah.
Yes.
Good. Shall we begin? So, welcome everyone. I would like to welcome all of you in the name of the organizers to the 2021 MESON conference, which is rather unusual. We were originally planned for 2020, as everyone knows. We've switched to this year in this virtual format. I think this is something people have learned to deal with in other conferences before. So I don't see this as so experimental, but anyway, I'm glad that we have so many people. We have 211 people registered for the conference this year. That's a very good number. I would, of course, much preferred to meet you all here in person in Krakow. It's been so nice to have the chance to sit together and just discuss with people. It's a bit more difficult online. Nevertheless, here we're together to discuss our science. That's our main point of being together. And we have a very excellent lineup of talks for the next 4 days. I must say I'm very happy that we are now seeing signs of, I would say, hope, perhaps uneven, but hope that we're moving towards some new type of normal that we can proceed with, and then we can really continue the work that we're doing. And that's all very good. There have, of course, been many changes to beside the world, also here more locally, the MESON conference. On the one hand, on the level of the people organizing this, we've had a kind of a generation change to the organizers of the MESON conference. Some of the other organizers will also say a few words now here at the beginning, but also some of the founders of the conference. There's been a change, and Anthony, directly following me, will say a few words to this topic. In any case, I'm just looking forward to these days, and I am very curious about all the new results that people have been able to put together in these unusual times. So, Anthony, I would pass over the word to you.
Thank you, Jim, very much. So Jim was representing this international part of the conference. There is also Krakow part. So it's Piotr Salabura and myself. I represent the Institute of Nuclear Physics. So we were always in this conference from the very beginning. So dear friends and MESON fans, so it is a pleasure to welcome you in the name of Institute of Nuclear Physics. So this is our 15th conference in the series. And in this context, I want to mention when it started. It started beginning of 90s. Unfortunately, many of you probably know, but many of you probably do not know that Professor Lucian Jarczyk, who was I can say a founder of this series. He started this series, really, he initiated, this was his initiative that the whole community decided to have this MESON conference. And what is unusual, this MESON conference is always in Krakow. So I want to say that we present organizer, all organizers of the MESON conference are really deeply indebted to Professor Jarczyk, who initiated this seriously, and he was always with us. He participated in all conferences. I don't remember. He was always there. So big thanks to Lucian. I can say that 2 weeks ago there was a special session at the Jagiellonian University devoted to Professor Jarczyk, and we shared some memories of Professor Jarczyk. I think it was a nice meeting, and we deeply miss him. Maybe I will say a few words about what we have in Krakow. Actually, in Krakow, we have as many as 5 institutions where people work on different aspects of meson physics. So I will start from Jagiellonian University, represented by Piotr Salabura. I am representing Institute of Nuclear Physics. But in addition, there's also Technical University, AGH, where also mesons are discussed and several works are going on. There's also Polytechnical University, and even there is a small group at Pedagogical University, small theoretical group at Pedagogical University, where also people work with mesons. So really many groups. I will mention about my institution because Piotr will mention probably about a university. So in my institution, we work on structure and reactions, low energy and high energy aspect of meson physics, elementary reactions and nuclear reactions, and theoretical aspects and experimental aspects. So really, in our institute, we are working on all aspects related to mesons. I welcome you in historical town Krakow. So usually I was telling some stories about saints and churches about Krakow, but this time you have no chance to visit all these places. As Jim mentioned, we have more than 200 participants who registered, and I hope that all of them will be participating in the talks and also take part in the discussion. So I wish you a good virtual time in Krakow. Thank you.
Okay, so now I think it's my turn. So in behalf of our Jagiellonian University, which was already mentioned, I also would like to welcome you to this meeting. Of course, we regret very much that there was no chance to meet in person, especially in our wonderful aula, Collegium Maximum, which you could visit in last years. I mean, as a small substitute of this, we have now in our breakout rooms an on-live stream from the market square and also Wawel Castle. So I hope you could at least enjoy the atmosphere of Krakow, looking to this live stream and have a coffee or a tea or a beer even, and feel like we were sitting in some beer garden on a market square, which actually was opened this Monday. So in Poland, this anti-COVID regulation are kind of relaxed now, so we are allowed to go to have some refreshment on the fresh air and our restaurants. So, well, that is a small substitute, as I said. So I also would like to welcome you, and also in name of Catalina Cuceanu from ENFN Frascati, which is also one of co-organizer of this conference, and unfortunately she could not join today the conference, but of course she welcome you as well. Yeah, so I think we are looking very much forward to this conference, which is quite dense and I think very interesting in topics, as you could see. So actually we were planning to make only some sessions with plenary talks, but actually we got so many feedback from a community that you could see there are even parallel sessions. I hope that everything will go well with this Zoom platform, and to assure this also that you are all now informed about technical details, how to switch between different rooms and how to switch also to this live stream from Market Square and so on. Maybe Damian, if you are now on, maybe you can say a few words again. There were some, I think you sent already some explanation and to the people, but maybe you could just make short intro to most essential things, how to stay on the plenary sessions and how to go to parallel sessions.
Yeah, sure. Rafał sent information about it, but in short, you should have a button called breakout rooms at the bottom of the screen. Then you can choose which room you are at now. And there are rooms for all parallel sessions and 2 for breaks called Main Square and Wawel Castle. And the main room, which is unnamed. And you can easily switch between rooms. And every time you can just click blue button of the left bottom corner called leave room, and then you will be in the main room where we will have all these plenary sessions. And if you don't have breakout rooms button, that means that you have too old Zoom application, but always you can use web browser to join us, and there will be everything working just fine. So if case of any problems, you can just chat me or email me, and I will try to help you. I think it's all.
All right. So I think there's also a live stream going on YouTube, right? Which people could.
Sure, yes, but only plenary sessions.
Only plenary sessions. So you can always tell this to your colleagues that those who are not registered, they have also a chance to see online and hear online the talks, which will be given on during the plenary sessions. Yeah, I think so. That's all from our side. And yeah, I think we can move slowly to the first session. We have also 4 minutes of time, so maybe somebody has some questions to the organization part, if something is unclear. Seems to be not the case. So yeah, I pass now the word to Jim, who is the first chair of the first session.
So thank you, Piotr. We're perhaps a couple of minutes early. Should we really start now, or do we have to wait a couple of minutes in case some people are coming at the last second?
We can wait, but maybe the first speaker can already try to see if everything is fine and he can share the screen and so on, that we are sure that we are well prepared to the first session. Okay, so then I would perhaps announce our first speaker is Umberto Tamponi. He will be speaking about Coconium at Bell 2, coming from ENFN Torino. Your screen is being shown perfectly, so I think excellent. Technically, we're all on track. Wonderful.
Can you also hear me clearly?
Yeah, a little bit quiet.
Okay, that's something we can fix.
And now? Now the microphone's out.
What about now?
A little better, yes. Fine.
Okay. Okay, let's give it like
Good.
this.
And I'd like to thank you for uploading your slides onto the web page. And then as a request to all the other speakers, it would be nice if you could also upload your files onto the web page. And then that way it's easy for people to download it who may have a poor internet connection or whatever. That would be useful. Perhaps also a few words to everybody. There are 30 minutes scheduled for each talk in the plenary session. This means about 25 minutes is expected that or is planned that the speaker can speak, and then I will make a sign when there's about 5 minutes left so that there's sufficient time for discussion. So please keep that in mind while holding your talk. Of course, if we're off schedule by 1 or 2 minutes, that's no big deal. But if we get off by a large amount, then in particular in online meetings, that becomes a bit more difficult to deal with. So we'll have to try to be relatively strict to the allotted time that we have. Okay, I think we get started now. It's almost exactly 12. So then, Umberto Tamponi, I would ask you to please hold your talk. I'm very curious.
Thank you very much. I hope I will satisfy your curiosity. So it's a pleasure to open this conference. Actually, it's also the first time for me, I think, opening such kind of conference with such talk. So I had plenty of introduction already, so let's go with the outline of this talk. I will basically talk about 3 different things. I will give you an overview of the BEL2 experiment, just in case you are not familiar with how it's set up and how it works. Then I will show you what we are doing right now for what concerns the quark physics program, both charmonium and bottomonium. And then I will sketch the plans for both the next couple of years and the next, hopefully, 10 years of data taking. So let's start with, of course, a bit of history. You know that the B factories were experiments at E+ and minus colliders. And despite being designed for doing for studying the weak decays of the B meson, they actually led to a number of discoveries in both charmonium and later bottomonium, even from the very early years of their operation. Here it's a summary of both Babar and BEL2. Altogether, we had order of 1.5 inverse attobar of data, which for reference means 1.5 billion BB bar pairs, because 1 attobar means roughly 1 billion of BB bar pairs. And you see how many discoveries were done over years, up to basically last year when we discovered the Y1075 in BEL2. This is a sketch of the data sets that these B factories collected. They operated mostly at the upsilon 4s energy, but they were also able to jump between upsilon 1s and even up to the upsilon 6s to do bottomonium spectroscopy, basically. For BEL2, we have a goal carved in stone about the number of upsilon 4s that we want, but we're still discussing about what to do for other resonances and other data taking. I will discuss about this in the latest part of the talk. So 1.5 inverse attobar was a data set of the B factories. 1 inverse attobar is Bell only. The goal of BEL2 is doing 50 times more than that. In order to integrate 50 times more luminosity in a sensible amount of time, your only chance is to increase the instantaneous luminosity of the accelerator. And that's why we moved from KEK-B to super KEK-B, whose goal is more than 30 times the KEK-B luminosity, which if plotted in this kind of famous plot in our community of instantaneous luminosity versus ear for different colliders, means jumping from here up to this point in 2030. The way in which you achieve such a dramatic increase in luminosity is by acting on 2 different parameters that are governing the behavior of your accelerator. On one side, you can, if you look at this formula and you forget about all these terms except this main one, on one side you can increase the beam currents, but you cannot do it much, so we only gain a factor 2 from that. The other thing you can do is to squeeze the beams, so you have, in order to have more dense beams, and we do it by reducing the so-called beta star function at the interaction point in the vertical direction by a factor of 20 in our case, which will lead us to have a vertical beam size of roughly 50 nanometers in the final configuration, and that's why this is called nano beam scheme. The 2 ingredients all together will give you the increase of instantaneous luminosity. While increasing the beam current is not so terrible, clearly diminishing the beam size is quite a challenge from the accelerator point of view. So we are doing a lot of works, the accelerator groups are doing a lot of work to establish this collision scheme. And that's the status in which we are now. We started in 2018, of course, with very low luminosity. With commissioning, we are kind of constantly ramping up the instantaneous luminosity along this trajectory that will lead us to our goal. But what makes our accelerator is quite pride is that the beta star function is decreasing over time, and we're currently running at we are currently running at 1 millimeter, which is the smallest ever achieved, but we even went below that. These are the current configuration of the accelerator. Well, 1 week ago, let's say. Now we have a little more than this. And we have integrated so far 150, 140 inverse femtobarns. We are keeping integrating, so this number will change and is changing right now. So the accelerator is performing quite well, I would say, despite the challenges of this new collision scheme. The problem is that having a completely new accelerator with increased luminosity and with increased currents and beam size will give you also increased backgrounds. In particular, we have to deal with two different kinds of backgrounds, the so-called single beam ones, which are there independently from having or not having collisions. And they are the two-shock background, the beam gas background, and the synchrotron radiation. You see that these guys here increase with either the current or even the current square. So this is going to be bad. The two-shock also increases with decreasing the beam size, which is kind of terrible for us. And then you have the backgrounds which are coming from physics process related to the collision. So low-angle bulbas, sorry, high-angle bulbas in which the electrons are down the beam pipe. Two-photon processes in which you have a very low Q-square reaction. So you have soft particles produced in the center of mass. And then you have the injection background. All of them increased except perhaps the injection background. So what you have to do when you have this situation is to redesign your detector in such a way that the degradation induced by the higher backgrounds are compensated by better performances of either the hardware or the reconstruction or possibly both. And that's why Bell was replaced by Bell 2, which is hosted in the same physical structure. So the magnet is the same and the heavy iron parts are the same, but the core content has completely changed. The tracking has been completely redone. We have a much better vertexing now with pixel and silicon strips here in the very, very core that you probably cannot see. We have a new drift chamber for general tracking that goes to lower transverse momenta, and it's also a larger radius. The calorimeter is the same, but with new electronics. The particle identification is being completely redesigned from scratch. We moved from time of flight and threshold Cherenkov to time of propagation counters and imaging Cherenkov. And also the muon system has been improved in order to cope with the higher rates. So new detector, new experiment. Let's see how these two things go together. By design, this is what we were expecting. We expect a better tracking from different point of view, both resolution, efficiency, and vertexing. You have here a reference for the tracking performance in Monte Carlo compared to Bell. We have a better full event reconstruction, which we call full event interpretation. It just means that we are better than Bell at reconstructing both the B and the B bar meson, which is quite important if you do weak decays of B mesons. For neutrals and particle identification, we are barely able to compensate with increased backgrounds. However, we are working on a better reconstruction, also using neural networks, of course, because it's 2021, in order to overcome our design, to do better than our design and achieve better performances than Bell. So this is the idea, and this is where we are. We have this rough sketch of our timeline. In orange, you have the peak luminosity of the accelerator. In green, you have the integrated luminosity. You see that we are set now to reach the 15 inverse october around 2031, with a couple of long shutdowns along the way in basically next year and in 2026 in order to upgrade either the detector or the accelerator. We plan, however, to reach the Bell luminosity before the long shutdown one, which means before summer 2022. I will probably keep repeating this milestone over and over because it's quite important for us. And it's quite important for the MESON spectroscopy program. So keep roughly in mind these dates. The point is, now that we have this long plan up to 2031, that we won't have as much data as well until next year, we only have 100 inverse femtobars. What can we do now? So of course we are doing a little bit of physics, but most importantly, we are understanding our detector and its performances. We have a number of studies coming up, which are covering hopefully all the aspects of the detector. I'm just showcasing a few of them I'm personally proud of. We have a better particle identification at low transverse momentum due to the fact that our silicon tracker is now providing a PID, which wasn't the case for Bell, and you see how well we can separate protons and pions at momenta of 100 MeV, basically. We have a quite good lepton ID, which is matching the performances expected by the Monte Carlo and has a quite low fake rate. You see here, the fake rate has been increased by a factor of 3 just for showing. The tracking is behaving exactly as the Monte Carlo is predicting with very low systematics. And we're also doing quite a number of studies about the trigger, because now that we are in the, let's say, low luminosity phase, low instantaneous luminosity phase, we can afford to keep the triggers more open in order to do more physics beyond the hadronic physics that we should do, that we are planning to do generally. So this leads me to this next slide, which is what we're doing besides performances. As I told you, we have looser triggers because we're running at low luminosity, which allowed us to do a search for axion-like particles and a search for invisible decaying Z bosons. These are both final state with a very limited number of tracks, so they're going to be suppressed by the triggers when we have to increase the luminosity and cope with higher Babbage background, basically. But also we are exploring new methods to improve over Bell. We have this paper coming up 2 months ago, in which we redo this quite famous analysis by Bell with a different method that basically gives us the same sensitivity despite having 20% of the, or even less than Bell luminosity. We also have more papers in preparation, so despite the low luminosity, it's not only performance, it's also physics that we're doing. Okay, so this was the overall status of Bell 2. I hope I convinced you it's a working experiment and we're doing things. Now let's look at what's happening on the quarkonium side of Bell 2. So classic introduction to this topic is how do we produce quarkonium? It's quite different from other hadronic colliders. Basically, we have to separate quite clearly from the experimental point of view bottomonium and germanium because they have completely different production processes. For bottomonium, we can exploit these 3 kinds of process. First of all, decays of the upsilon-4s via the emission of mostly an eta meson that gives you the HB1P. And this is basically a gateway to the spin singlet state. So 1 plus minus, and then the HB1P decays to eta B1s. This is a completely new thing that was discovered only in the late years of Bell. Then we have the ISR production, in which you collide at upsilon-4s, and the radiative correction will lower the center of mass energy to a narrow bottomonium resonance. Of course, you produce only 1 minus state. And then you can also tune your beam energy in order to collect data at whatever resonance you want. For germanium, we have also the ISR production. Of course, it's quite important. We have the germanium production in B meson decays, which allows you to access basically any quantum number. And then we have the so-called gamma-gamma fusion, in which you have 2 photons, either real or virtual, that give you a germanium state with quantum number 0 plus or 2 plus, whatever decays into 2 photons, basically. What's important from the point of view of organizing experiment is that the germanium program can be run, actually is run all the time at the upsilon-4s energy, so goes in parallel with the B meson program. The bottomonium program usually needs dedicated run because you want to move to the resonance you want to study. So it's an alternative to the BDK's program and requires some dedicated beam time. So when can we have some new results given this experimental constraint? So spin singlet bottomonia from the upsilon-4s and germania is something that does not require changing beam energy. We just need to integrate more data. So I would say that by the time we reach 1 inverse octoban, we'll have new results on HB1P and eta B1s. And by the time we reach 2 inverse octoban, we'll have more results from everything germanium. Concerning the bottomonium program that requires running at non-4s, the amount of luminosity is much smaller. we are of the order of 200 inverse Venn both for the program above 4S, so study the exotica in the 5S and 6S region, and the program below the 4S, so studying the narrow bottomonia. However, we have not scheduled yet these runs, so I cannot tell you exactly when they will take place. So given these other extra constraints, you may wonder what we are doing now, given that we are here, very far away from these thresholds. What we're doing is doing rediscoveries. It's kind of not that much exciting, but it's, I think, a very important exercise we have to go through to demonstrate that our physics program is healthy, our detector is working, and we know what we're doing. So the first thing you want to rediscover is probably the X3872. In this case, you reconstruct B2K pi J psi, and you explore different regions of the invariant mass of the pi J psi system. You expect to see the psi prime, and this is exactly what you see in this plot, a very nice peak of psi prime. And if you move sideways from the psi prime in the X3872 region, you also see a convincing peak of this resonance. So we can claim a rediscovery, which is nice for us. But more important, we can measure this branching ratio and check that it's within the statistical uncertainty, which is quite large, within, it's compatible with the PDG value. So we don't have a complete misunderstanding of the efficiency, and our detector is working as expected. Also, the resolution is what we expect, the mass is what we expect, and everything is fine. We just need more statistics. Of course, we don't only do charmonium, we also do bottomonium. In this case, the standard candle for the reconstruction are the dipion transitions from the 4S. The final state you reconstruct is plus and minus to pi plus pi minus, and then a high mass mu plus minus pair, which is either the 1S, 2S, or 3S resonance. And then you ignore whatever photon you're missing. In this way, you catch two physics processes at once in one plot. You have the direct dipion transition from the 4S, which are sitting here on this band. You see 4S to 2S, 4S to 1S. But you also catch the dipion transition among narrow bottomonium states, which are produced via ISR. For example, this guy here is ISR 2S, and the 2S decays to pi 1S. So you have a global check that all your efficiencies are fine. And if you compare with Bell, you can also see that we finally observe the 3S to pi 2S transition, which is very low transverse momentum in the dipion system, which was not catched by the default Bell tracking, while it's catched by our default Bell tracking. So things are getting better on the tracking side, and we see it in the data as well. Now, time for discussing programs and plans. I know rediscoveries are not so exciting, I guess. But we're not only doing rediscoveries, of course. We know that by 2022, so within 1 year, we will have as much data as Bell, meaning that we will be able to both redo the analysis done by Bell or combine with the Bell analysis to get a better result. In many cases, we can also just have better results because we use new techniques, we had new ideas in the meanwhile, and so on and so forth. Of course, if you want to be ready by 2022 and have analysis and papers out in 2023, you have to start now. So we have a number of running analyses, which are already looking at Monte Carlo, sidebends in the data, or whatever else you can do without opening the box, in both charmonium and bottomonium. In charmonium, in particularly, I would like to stress the X3872 line shape, which is a combination of Bell and Bell 2 dataset in order to reach a couple of inverse octogram, and the study of B2K charmonium inclusive. In this case, you reconstruct the B meson. Sorry, you reconstruct a B meson that recoils against this guy. You reconstruct the kaon, and then you look at the recoil mass against the kaon, and you should see the various peaks of the charmonium system. This is very important because it was done by Babar, and they have, I think, just an evidence for the X3872. But if you measure this precisely, you will be able to access the absolute branching ratio for the X3872, and also other states, of course. In the bottomonium case, our golden modes for this early data taking are the analysis of the Dalitz plot of 4S to pi 1S, And whatever study about HB1P and eta B1S, in particular, it's exclusively case in few body, just to try to start understanding how these guys hadronize, which is a completely new topic. However, it's not given that we have to wait for one inverse autobarn to have something relevant, or even 2023. If you look at the spectrum of bottomonia, and you check how much data we're taking at different resonances, you will see that there are places like the 3S or this Y1075 here, in which we only have order of few femtobarn, inverse femtobarns. So even just taking 10 inverse femtobarns there would give you a huge advantage and will give you a number of new publications that could supersede the Bell results. So one of our plans for the very near future is to take more data at the 1075 resonance. So the 1075 resonance is this bump here, which has been observed by Bell in the upsilon 1s pi pi, upsilon 2s pi pi, and upsilon 3s pi pi cross sections. It lies between the 4s, which is around here, and the 5s, and has a number of theoretical interpretations. What I think is quite interesting about this guy is that it sits here quite far away from any S-wave threshold for meson and anti-meson systems. So I would say naively that it's not easy to accommodate it in a molecular model, even if I'm sure that people are able to do that. And it's also quite far away from any quark model prediction for the 3D states. So it might be a tetraquark, it might be a mix of tetraquark and vector and conventional quarkonium, we don't know. And we have to investigate more in detail. So the plan that is now under discussion within the collaboration, it's not been approved yet, is to take data at 4 different points around the 1075 region before the 2022 shutdown. So let's say February next year, just to give you a very rough reference. And the idea would be to take 10 inverse femtobarn on the peak. You have to keep in mind that every one of these points is just one inverse femtobarn of Bell data, so it would be 10 times more. And then take a few inverse femtobarns in these points here, which will allow you to pinpoint better both the pi pi upsilon cross section and the open B meson cross, sorry, the BB bar cross section, so plus and minus 2 BB bar, BB bar, B star B, and B star bar. We hope to get this program through and to convince the rest of the collaboration and have this data set by next year, basically. So let's go to the last part of my talk, which is looking even further in time. Plans for what I call 2024 plus, but I have to say that this number might be 2023, might also be 2026. We don't have any concrete discussion about this timescale yet. However, one thing we want to do is definitely to take a fine-grained scan of the region above the 4S. I already showed you before that we have seen this 1075, and this early data taking would be a preparation for that. But what we want really to do is to go in 10 MeV steps, or even less than, or even 5 MeV steps across this region and take order of half inverse autobarn in total. The goal here is to measure the decomposition of the R ratio. So see if the exclusive channels, the exclusive processes saturate the inclusive cross section and how they do it. We already started doing it in Bell. You see here the black points are the scan by Babar, which we want to do with higher statistics, and the red points are the scan by Bell, which was much more spaced. And the Bell data are showing you BB star and B star processes summed together. The black dots are the inclusive cross section. You see that they basically saturate, the exclusive process saturate until this point here, which is where the B sub S star threshold opens. And the 5S and even the 6S are basically not described by these processes here. So we would like to have all the pieces of the puzzle all together. The problem, of course, is that this is challenging for the accelerator because it needs to push up to the accelerator limit, which is roughly here at 11.02 GeV, sorry, and also have a good understanding of the accelerator performances across the sky. Another thing we would like to do is going in the opposite direction and move from the 4S down to narrow bottom-only. In this case, either 2S or 3S, we still have to decide. The goal here is, the goals here are two. On one side, we want to study new physics channels. In particular, I feel that it's very important to measure the lepton flavor universality in the upsilon decays. So basically, you measure the ratio upsilon 1s to tau tau over upsilon 1s or 2s or 3s to mu mu. Because there are papers which are relating this ratio to the RD star anomaly, or basically any other evidence for lepton universality evaluation. Okay, this is the status of the measurements so far. We have quite old measurements of this ratio by Clio, which were slightly above 1, and these Clio points are kind of all correlated all together. Then we have an upsilon 1s measurement by Babar, which sits here. But last year we had an upsilon 3s measurement by Babar with a new technique, with reduced systematics. And you see it's going in the other direction with respect to the previous one, and it's falling exactly in the region where you would expect it to be, given that the RD star anomaly is real, according to this model at least. So this plot is really screaming for more data and error bars reduced by a factor 3 at least, to see if we are really at least 3 or 4 sigmas away from the standard model or not. The other thing which is important to do is upsilon 1s to E tau or mu tau, or also E mu, so lepton flavor violation. The reason is that according to this paper by Petrov and collaborators, these modes will give you a very strong lever arm on the Wilson coefficients of the effective field theory model, much more than other processes with lower mass mesons. And then I have two personal favorite QCD goals. This is really just me and what I like to do, which are studying the upsilon, which is studying upsilon 1s to multi-quark system plus X, so inclusive production of multi-quark system from the upsilon. And the reason is that we know that we are producing the X3872 in PP bar collisions. We know it from many experiments. But the only kind of, not really similar, but the only complementary process one could imagine in which have an inclusive production is bottom-volume annihilation. So we have a paper that shows, done by Bell, that shows the upper limits for the production of all these exotica. But if you take the ratio between this upper limit and the production of psi prime, you see that we are still above what is seen at LHC for the X3872. So basically, we would like to push these numbers down below to 10 to the minus 2 and see if we see production of exotica, especially the X3872, or if we don't, and if we see it, with which ratio to the psi prime we do it. And finally, there is a search for dibaryons, which is a thing I'm personally involved into, both loosely bound, in which dibaryon decays to either lambda proton pi or lambda lambda. The analysis by Bell might be inconclusive. We are still discussing about that. And then there is a search for deeply bound dibaryons, so basically invisible final state that recoiling against the lambda lambda pair, which is kind of was done only by Babar, and it's kind of inconclusive because they analyze only a very limited number of final states. So this is my conclusion. I think I'm over time already, so I will leave it here. Just keep in mind that we're running, and first result will come in 2023. Thank you.
So thank you very much. Indeed, we did go over 1 or 2 minutes, but it was good to see also the outlook at the end for these upcoming measurements. So we can take a couple of minutes for questions. Is there anybody who would like to speak? I think the best would be you raise your hand, and then I can call on you. So Zhang Yangxi, please go ahead.
Hi, I'm about to very next slides. I have a question about for Bio2, do you have a significant improvement of the mass resolution compared to Bio actually?
Of mass resolution of...
Or momentum resolution, similarly, yes.
So in general, you mean? Generally speaking, we have a better tracking resolution, so also the master resolution will improve. However, it's a kind of second order effect. I mean, yeah, we will have a slight improvement in master resolutions in general, but not the factor, not the factor 1.5 that we have in tracking resolution.
So I'll say comparable, let's say.
Yeah, okay, you will get, I don't know, maybe 10% better resolution, not a factor 3.
Okay, thank you for that. Anthony, you've raised your hand.
Yes, thank you. Slightly different topic. I wanted to learn if there is chance that you study also gamma-gamma reactions to several quarkonia. There is also interest in such a process.
Oh,
but you didn't mention about this at all.
You mean gamma-gamma production for charmonium?
Yes, exactly, and studying transition form factors for charmonia, for instance.
Yeah.
Eta C, eta C1s, 2s, chi C.
Yeah, that's part of our program. I mean, we have a long paper with all the physics program that we want to do. However, I'm not aware of any early analysis of those data sets, of those channels, sorry. I think that we'll start looking into them once we have a couple of inverse Sato-Barnard data.
Thank you.
Okay, let's take a last question. Vadim Baru, please go ahead.
Thank you. I have a short question. When do you expect to have bothrombinium decays from Y5S? And maybe do you have plans for upgrade to Y6S?
So Y6S is already in our within our reach. Yes, here we go. Y6. So this plot is complicated. However, you have to look at this red thick line and the first vertical line. These are the constraints from the accelerator. The hyperboles here are the square root of S values. So the 6S is already reachable at the very, very edge of the accelerator performance. So that's not technically a problem. The problem is when to allocate beam time for that. And we have not discussed it for before long shutdown 1. So it's a discussion we're going to have after 2022. Both 6S and 5S. But we definitely want data at both resonances.
All right, thank you very much for this very nice talk. I'm glad to see that you're up and going, and there's such great physics that we can expect coming up very soon.
Thank you.
So if you could please stop sharing your screen, thank you. And then now we will continue. Zhang Yangshi will present results on exotic spectroscopy from LHCb. Please, go ahead.
Okay, James, do you see my slides and it's moving?
Yes, perfect.
Okay, good. So I'm very glad to discuss with you about the LHCb result on exotic spectroscopy. Thanks for the opportunities. So why do we study that? As already mentioned in the previous talk, so basically involved in the region of QCD. In fact, the QCD is involved in all aspects of particle physics. And we all know that QCD is less known compared to other parts in the standard model because it involves both perturbative, which we can calculate the process in a good way, but there are also non-perturbative regimes of QCD. So we have to rely on some models, which is less precise. In any day, we want to have a precise measurement of standard model. We have to control QCD. From the recent update of the GMU-2 studies, we can see that the new uncertainties is at the same level of standard model calculations. When the uncertainties from experiment reduced in the future, we also have to control a theoretical uncertainty, which is dominated by the QCD contributions. And the experiment which is essential in this region. Okay, so how do we do that? In fact, as we know that I mean, when we just go by studying the light spectrum in the atoms, we probe the dynamics of the electromagnetic magnetic interactions. Similarly, we can do the same thing by studying the hadron spectrum, which help us to understand the non-productive dynamics in the hadrons. So how quarks are confined in the low energy non-productive regime, according to Gamma in the week, we know that hadrons are formed from quarks in either a quark and anti-quark or three quarks, which are conventional hadrons. The quarks can also form hadrons in a more complex way. For example, tetraquark and pentaquarks, and so on, which is called exotic hadron. However, this is just a static picture of the hadrons. Want to know from the static one about dynamics inside. From the conventional one to exotic ones, there arrives a new problem, which is about the internal substructure. For the conventional ones, for any combination of the two quarks, they always carry the color charge, so there has to be a tight bond. While concerning the complex object, they can first form, like say, a color neutral one, then the color neutral object will form complex object, which is so-called molecular. On the other hand, they can also form compact states. So it's just called a substructure problem, which there are many debates about the newly observed states actually. So about short brief history of the exotic hadron. In fact, the first confidence signal was only discovered about 20 years ago from a bio-experiment, which is X3072. Now we know that its JPC is 1++, has the same quantum number as Ca1-2p, which is also labeled as Ca1-2p in the recent PDG. And its exotic behaviors is in a few aspects. For example, its mass is very close to the D0 star mass threshold. As a matter of fact, we don't know which is larger, and also its width is very small. For the moment, we don't know exactly which is the width because it's tiny compared to experimental resolution. Maybe some value below 1 MeV. And after that, many more states had been observed in the charmonium or potammonium regions, basically contain cis-bar or BB-bar quark inside. Even that, we don't have a clear pattern found about these states. As a matter of fact, we cannot predict precisely these states. Well, some experimental features, we know that these states has a mass from MeV to a few hundred MeV, and they can be produced either in electron positron colliders or from hadron or in B decays. Some of states are found to be very close to hadron threshold, for example, the X3072. So it motivates the theoretical interpretation of them to be hadron molecular, as I mentioned earlier. So recently, RC announced the discovery of 59 new hadrons at LHC. In fact, most of them are observed in RCB experiments, and despite most of them are conventional ones, there are still a few states which have exotic quark contents. For this slide, I will discuss the most recent discoveries by RCB shown in this green area. Okay, so before that, I would like first to give a brief introduction about RCB experiment. As you all know that RCB is constructed to study a high flavor, which can cover PT as low as 0, basically. So to detect heavy flavor hadrons, it's important to that we can restrict the secondary vertices, which is performed by so-called vertex detector, which can provide a lifetime resolution of around 50 picosecond, which is much smaller compared to a typical beauty lifetime around 1.5 picosecond, and because of that we can resolve the fast oscillation between BS and BS bars, you can see in this plot. Another important feature that we have very good momentum resolution, up to 200 GeV, we have as low as 1%. This allowed us to separate structures which has similar mass. a typical value for chipset at 3 GeV is around 50 MeV expanded resolution. For the study of exotic hadrons, for most cases, we have the K-ion proton in the final state. So it's important to separate these hadrons from the QCD background, which are mostly pions, which is performed at RCP using dedicated particle ID detector, which can identify K-ion proton with a efficiency of about 90% in a large kinematic range. And in this case, also the MESON rate from proton to K-ion proton to be less, a pion to K-ion proton to be less than 5%. Similarly, for the Champonian final states or Boltzmannia, we have muons in the final states. We have good reflection efficiency. Also, we have good identification efficiency. For the muons below a few hundred GeV, the ID efficiency of 97%, while the MESON rate from pairs kept as low as below 3%. So it's important for studies, for precise studies of exotic hadrons. For the analysis, as shown later, we use all the data collected by RCB in round 1 and round 2, which is 3 infinite bar and 6 infinite bar, respectively. And in the proton protocol, it is very important that we can collect all BUT decays, such that we can study all different systems where exotic hadrons can emerge. Okay, let me first discuss about the study of pentaquark studies. I will cover two analyses. First about the chipset proton states, and then about the chipset lambda states, which is studied in the cascade B to chipset lambda K decays. As it is known that using round 1 data, RCB observed 2 states, basically PC 4380 and PC 4450 in the lambda B2 chipset proton K decays. And the PC 4380 has a mass has a weight around 200 MeV, which is quite large actually. And the other one, 4450, has a weight which is relatively smaller. The branch fraction is measured to be about 80% for the wider one and around 4% for the narrow one. The GP was not actually completely determined. There are 2 configurations which preferred, but the other configuration is not ruled out. These 2 states found their evidence in the similar decay mode, lambda B2 chipset P-pi, and also the narrow one is confirmed by the model independent analysis, which is actually not sensitive to the broader states, so it is not reported in this analysis. Using round 2 data with improved luminosity and also improved selections, total increase of staticity is about 10 for the lambda chipset PK decays. Since we have so many decays, we can focus on the narrow structures. In this case, the interference can be ignored at the leading order. Basically, only one-dimensional environmental distribution of chipset proton is studied, and to reduce the contribution from lambda star randomness, we apply veto by only looking at the mass distribution with proton K above 1.9 GeV. You can see this plot where we vetoed mostly the lambda star contributions. Okay, so looking at the spectrum after the selection mentioned previously, we see there are basically the 4450 structure is there. There's additional one which is 4312, and the 4312 has a significance of above 7.3 sigma. And we found that the 4450 is actually preferred to be 2 peaks rather than 1, with a significance of 4.5 sigma. Because it's only one-dimensional analysis, it is not it's not sensitive to the broad structure, the one mentioned earlier, 4380. Nevertheless, we perform a fit with or without this state. The data can be described with comparable fit quality. So we cannot say it is not there or it is there with this only one-dimensional fit. The mass and width for the three narrow states is measured. You can see the width is around 10 MeV for the 4312 and 4457, and for the 4440 is 20 MeV. It should be noted that the first and the last state, they have the mass which is very close to the sigma C D0 or sigma C D star mass threshold. So it motivates a few studies interpreting them as hidden moleculars of these sigma C and D states. Okay, so come to the Cascade to just lambda study CB. Actually, this is an analogy to the LMB to JEPSI PK states. PCR states was predicted by many theoretical calculations, and it is possibly produced in this decay mode. As we studied the decay using full data, in there are about 80,000 signals detected. And you can see from Dali's plot distribution, this decay dominated by two cascade states, cascade 60-90 or cascade 80-20. Nevertheless, we performed an amplitude analysis to study the different structures. In fact, we only need a few components to describe data because studies are very limited. In the end, we found evidence of JEPSI lambda structure with a mass at 4460 MeV with significance around 3 sigma. The mass of these states is found to be about, you can see 100 MeV higher compared to the PC 4450 and with around 20 MeV, which is a very narrow state. As a matter of fact, this state there are around 10 states. There are 10 states predicted in the sigma in the Cascade C D star molecular model. 2 of them has a mass which is close to the states we also observe in this decay mode. You can see on the right hand plot showing the fit model is state of the evidence of the by RCB and the two threshold Cascade C star with a different spin. They are just basically they are overlap in the same region. Okay, now come to the study of tetraquark states. I will include 3 studies: the structure in the JEPSI mass spectrum, the D-K structure in the B2 D plus D-K decays, and also the JEPSI and JEPSI structure in the B plus 2 JEPSI 5 decays. The dead JEPSI structure is observed in a sample of around 34,000 dead JEPSI signals. You can see here we have very little background actually in the sample after the selections. That vital JEPSI from B and pi up background. According to a previous study by SB, we know that for the production of the JEPSI signal inclusively, there are basically 2 components. One is double pattern scattering, where the 2 JEPSI mesons are produced from 2 uncorrelated pattern scattering, or from single pattern scattering, where the 2 JEPSI from the same pattern scatterings. For the DPS, it is expected that the mass spectrum of the depth JEPSI is smooth, while for the SPS, it can produce either both smooth continuum mass spectrum or produce resonant Fock quark structures. Also for the SPS, production is expected to have a larger PT compared to DPS, which is explored in this analysis to enhance the signal. Okay, now comes to the JEPSI mass spectrum. Shown in black is the case for both JEPSI in the signal region. Shown in blue is the case where either JEPSI is in sideband, basically the background. From the spectrum for JEPSI signal, we see there are basically a few structures. One close to the JEPSI mass threshold, which is broad. In the region between 6.2 and 6.8 GeV. The other one is narrow at 6.9 GeV. There's a hint of another structure at 7.2 GeV. by comparing the GIPSI signal and GIPSI background, we see there's no basically no obvious structure in the case when at GIPSI is background. Also, the structure in the signal is not caused by any detection effect. If you look at the detection efficiency as a function of GIPSI mass spectrum shown on the right-hand side, you see the efficiency is rather flat with only marginal variation as a function of the mass. Okay, to understand the property of structure, we perform a fit to the GIPSI mass distribution. According to the discussion earlier, we know there are 3 different components. The DPS production, which is smooth, the smooth SPS production, and also picking structure. For the DPS, we construct the distribution using the connected from the single GIPSI production, assuming that the 2 GIPSI is uncorrelated. Where for the SPS smooth SPS contribution, we describe it by using empirical function, which is a two-body phase space multiplied by exponential function, allows the variation of any production mechanism. For structures, we consider 3 components describing the one at the threshold, the narrow one at 6.9 GeV, and the one at 7.2 GeV. For the one at threshold, we found that we need 2 weakness to have a good description of data, and the significance of structure is found to be above 6 sigma. Similarly, for the 6.9 GeV, a broad weakness is good enough to describe data, and the significance is found to be above 5 sigma. While for the one at 7.2 GeV, significance is found to be very low, is below 1 sigma. For this model, we match the parameter, randomness parameter of the structure at 6.9 GeV, with a mass of this value, and also weights around 100 MeV. We tried several variations of this model without any interference. We found that it is difficult to describe the deep at 6.8 GeV, which suggests that there's some we need some alternative model to describe data in this area, which is actually described by introducing interference. For the model shown in this slide, basically we introduce 2 Brownian functions. One Brownian is used to describe the threshold structure, and it is interference within the SPS smooth components. That structure is used to describe the narrow 6.9 GeV peak, which is standalone added incoherently with other components. For this model, the fit quality improved from basically chi-square probability from 5% to 60%. And you can see also the deep with well described, and also the broad Brownian function sits right on this deep actually. It should be noted that it is not the final answer of the mass spectrum, as in this case, we assume that the whole SPS component has a single JP contribution, because we ask it to ask the whole component to interfere with the Brownian function of a definite JP. In this case, the narrow peaking structure has a mass which is different, but still consistent with the previous model, but the width is much larger to have better description of the deep. And you can see for the broad Brownian function, the width becomes around 300 MeV, which is quite huge. Okay, we also tried other variations to describe data. For example, we use a single Brownian functions to describe the threshold structure, and another one to describe the 6.9 GeV peak. The chi-square probability reduced to 1%. Or we use only one Brownian function which interferes with the SPS smooth component to describe data. Also, the fit quality is reduced from 60% to 3%. We also considered the case that the structure at the threshold is due to the feed down from excited Chamberlain state. For example, gypsy, where the Kc the Kc decay to gypsy gamma, the gamma is not detected. We found that this can also describe data with similar field quality compared to the one without the interference. In the last case shown in this slide, we include explicitly a Brownian for the 7.2 GeV peak to study the variation of the field parameters for the narrow peak. It's found to have very little impact actually. Okay, so a summary of the fitting, we found that there's non-trivial structure in the spectrum. Where for the threshold structure, we can describe it with either one Brownian, two Brownian, or with a function which describes the field down from exact states, while the fit with interference is preferred over that without any interference. The structure at 6.9 GeV is consistent with the Brownian with or without interference with the SPS component, and it reported as axis 900. A measure production of this narrow structure. Actually, the production times Brown fraction of the gypsy final states over that of inclusive with the gypsy production is around 1%. It's only a tiny component. So if this is true, it will be the first candidate of a fully charmed tetraquark. Actually, its existence is predicted as early as after discovery of charmed quark in the 1970s. Recently after the discovery of many new exotic hadrons, this data have been restudied using dicharmed quark models. In this case, it's apparently a compactly bound. According to literature, for the structure at threshold, it's interpreted as in the region of the ground or P-wave states, while for the narrow structure, it is interpreted as a P-wave or D-wave states. But it's not. They don't have a same answer according to different literature. So it's important to perform a GP study in the future to give more information about this. So for the now comes to the B2 B plus to D plus D minus K decay study at CP. Actually, for this stage is quite special. The conventional hadron contributions can only happen in the D plus D minus, which is charmonium. There's no conventional D plus K plus or D minus K plus hadrons in this case. However, by using only conventional charmonium to describe data in a model independent way, they cannot describe very well. In particular, in the D minus K MS distribution around 2.9 GeV, there's a strong discrepancy, while in other dimensions there seems to be described. So empty analysis is performed to disentangle different components since all the final states is scalar particles. So the parity and the spin of the random contribution is completely determined. So you have, for example, you have 0 plus, 1 minus, or 2 plus. So with only a conventional charmonium, as I mentioned earlier, it can describe the D plus D minus data in the low mass region, but not the high mass region, which has a larger contribution from the one from the peaking structure in the D minus K plus spectrum at 2.9 GeV. Also, apparently, the peak at this 2.9 GeV is not described well. It's true. We note that by trying different variation of the fit model, it found that the reflection from the conventional charmonium is difficult to describe this narrow structure. So in the end, we have to add two D minus K plus structures to describe data. One has a JPU 0 plus, the other one is 1 minus. You can see after the inclusion of the two structures, the data in all dimensions can be described very well. In the end, the 0 plus state is found to have a mass around 60 MeV, while the other one, X1, is found to have 100 MeV. So we notice that for the X1 state, you can see it has around 30% contributions in this decay mode to D plus D minus K. So it's very unexpected actually. So for the last topic about B plus 2 JPSI-5K decay, in the total sample in RSB with round 1, round 2 data, we have around 24 signals, which is the largest sample of this decay model in the world. By inspecting the distribution, we found obviously there are 4 structures in the JPSI-5 mass spectrum, and there's a broad structure in the JPSI-K spectrum. We should also consider the K-star resonance decay to 5K actually. So in end, we perform 6-dimensional amplitude analysis to this decay mode, considering all 3 different contributions of resonances. So for the conventional K-star decay to 5K, the inclusion of state in the amplitude model is guided by these predictions. For those states that were established, the mass and weights are fixed to the known value, where for this that are confirmed by experimentally, the mass and weight parameters are floated. In the end, there are 9 states. The 9 K-star states has found the significance about 4 sigma. So they are considered in the default model, where others are not significant. So they only considered as systematic test. So for the X2JS5 contributions, actually the same decay has been studied by CDF, and 2 states was reported. One is 4140 with significant about 5 sigma. The other one is 4270 has a significant of 7 sigma. It's about 12 years ago, and the 2 structures were confirmed by CMS a few years ago in the same position. It's noted that it's just a 1-dimensional analysis in the JPSI-5 mass spectrum, and no interference or reflections included in the study of the line shape of the 2 structures. Well, for the JPSI-K dimension, the ZCL states is expected in analogy to the ZC states taken to JPSI of psi2s pi. There are several states observed in B decays. For example, for the 4430 and 4200 observed in the B decays. Similar states also observed in plus E minus machines, for example, ZC 3900. Recent experiment reports the observation of the ZCL states in the D0, D star, or D star final states with mass around 3980 MeV and weight around 10 MeV. There's another experiment have similar evidence, even though these ZCL states are predicted by many models. So, and the amplitude analysis by RSB suggests that we need to 10 different JPSI X components to describe data. There are 8 X2 JPSI-5 components plus 2 JPSI-K components, which is denoted as ZCS. And with these 10 new components, the data can be described very well in all 3 dimensions. You can see it in slides. Okay, so a summary of these new states. For the 4140, which was reported by CDF and CMS, actually the mass becomes much larger from 10 MeV to 160 MeV. And in the same region, there's new JPSI-5 states with a different common number, 2 minus with respect to 1 plus, and the mass is similar, but the weight is also about 1 MeV. There are 2 new JPSI-5 states observed in the new analysis compared to the round 1 analysis. Besides, there are 2 new ZCL states mentioned earlier. They should be noted that this state is different from the one observed by BESS because they have much larger weights compared to the one at BESS. Okay, so to inspect how we need, why do we need this ZCL component, we can we can look at the mass distribution in 2 slices of JPSI-5 mass distribution. You can see the fit with or without ZCL states, the data are described very differently. With these states, we can describe well the JPSI-K mass spectrum as well as all the angular distributions. Okay, for the JP studies, you can see that for most of states, they prefer to be in the configuration that the optical angular momentum 0 is allowed, either 1 plus or 0 plus. One special case is of X4630, which has a 1 minus, which actually exotic JP, which cannot be constructed from a quark and quark. Okay, so I think I'm running out of time. I will go quickly this slide. So to interpret these states, one first interpretation may be to consider them as molecular states. And naively, I construct DS or DS star mass threshold for different states. It is think that either the mass threshold is very different from the observed mass, or the JP is different from the observed state. So the molecular interpretation of these states is not a natural case. On the other hand, one cannot rule out the interpretation of these states using conventional harmonium, because CC bar a conventional systematic unit size is actually not forbidden. While for the DCS states, there are many calculations already after the discovery. Some analysis interpret these states as U3 partner of the DCS 3900 and the DC4020. Using the molecular model, actually the mass is very close to the D star and DS mass threshold, and also the JP is not violated actually. Okay, I think I finished the allocated time. So I just I think I stop here. Just a summary of different analyses as shown in this slide. Actually, a lot of similar studies have been performed. As you can see, all these states have been observed in last year. So I think more studies will come soon in the very near future. Okay, thank you for your attention.
Good, thank you very much. Indeed, as a great statement there at the very end, that more studies are coming out, that raises our interest and attention. I see that Ologio has his hand raised. So please go ahead.
Can you hear me?
Yes.
Okay,
yes.
Thank you. So let me see, I mean, first a couple of comments and short. I mean, one, I mean, is concerning the GC0 to P, I mean, that you found 3,930 MeV overlapping the GC2 2,930. So I think this is very nice, and I like it, these results very much. I mean, in fact, there were predictions by Chang Zhao and others, I mean, that also said, I mean, the state should be there. And you know, this contradicts very, very much, I mean, the results, previous results, which are in the PDG by the Bell collaboration, silicon experiment, which says that the state should be at 3,860. I think these claims in the PDG are based on very poor, extremely poor data and a wrong analysis, as some collaborators, I mean, Xie Jun, Geng, and others have shown in the paper. So I called in, I mean, the responsible people of the PDG to think about that and eventually remove, I mean, that state from the PDG and replace it by the new one. Okay, and then the other thing, short comment, here I cannot be so praising, which is, I mean, the X4140, where you still claim you have a width so big, 162 MeV. You know, I think this experiment, I mean, and this comes from an analysis of the ZEP-Sci5, I mean, spectrum, in which you do not take into account the X4160. I mean, the analysis done putting the X4140, but the X4160 is not taken into account in the analysis. And the X4160 is wide. So again, if you redo the analysis of the low energy data by putting the two resonance, you can leave, and it has been improved, I mean, with an arrow 4,140, and the large width comes from the large strength comes from the 4,160. I think that should be revised. Yeah.
Okay, this is very good suggestion. I will think about it, but I don't know whether it is tried or not in the study. Okay.
Yeah, I mean, this is there to the right. Yeah, in the slide that you are showing there to the right are low energies, low and right. I mean, the figure low and right there are low energies. I mean, most of the strength comes from the 4,160, which is wide. But since you don't put that in the analysis, then you have to blame, I mean, the 4,140, and that's the reason why you get such a large width. But that's not correct.
Okay, I think we have to stop the discussion here. We've dramatically gone overtime on this talk. I'm sorry, Antoni, but I think we will end this here. So thank you again, Zhang Yangshi. I would like to now get the next talk started. Mark Pelitzaios is talking about recent achievements of BESS3. So Mark,
Yes,
please
hello.
go ahead.
Thank you. Let me try to share the window here. So you can see my slides?
It's fine, yes.
Okay, so yeah, thank you for the kind introduction, Jim, and thanks to the organizers for the invitation to this nice workshop and giving me the possibility to present recent achievements of the BESS3 collaboration here. So the physics program of BESS3 is very rich and includes as main pillars light hadron spectroscopy, and we can also investigate decay dynamics of the lightest mesons with high precision. Then if we move up in mass and energy, we can access the whole Shermonium range. Here, of course, we are further exploring the exact nature of the exotic XYZ states. And in general, we can study decays and transitions of all Shermonium states with high statistics and precision. So in open charm physics, we are about to investigate d-meson decays and d-bar mixing. And then the experiment also allows for many, to address many further important topics. But today, due to time constraints, I have to limit on recent highlights from light hadron and exotic Shermonium spectroscopy. So the experiment is located in Beijing at the Institute of High Energy Physics. More precisely, it's located at the Electron-Positron Collider BEPC2. The machine is operating in a center of mass energy between 2 and 4.6 GeV. And during summer 2019, it received an energy upgrade, so we can access up to center of mass energies up to 5 GeV. Over the time, the machine has reached its design luminosity, and all in all, it's operating well since March 2008. So it's also the best detector, which is closely surrounding the interaction point, and from the inner part of the detector to the outer part, we have a drift chamber, a time of flight detector, electromagnetic calorimeters, and the outer part of the detector consists out of a muon detector. So this allows to address, first of all, the data sample. So since 2009, the first physics months of BESS, the experiment has collected large data samples in the tau charm mass regions at various Shermonium resonances and other energy points of interest. So in particular, we have 1.3 billion J-psi events ready for physics analysis, as well as about 500 million psi prime events. Currently, we are taking more data at this resonance, and the goal is to achieve here 3 billion psi prime events. So E plus E minus annulations feature a very clean environment with low backgrounds, and therefore the experiment or our studies are complementary to the physics performed at hadronic machines. So with this, we are settled to address questions in spectroscopy. The ultimate goal is to map out the entire spectrum of hadrons. So besides conventional hadrons, which are mesons and baryons, QCD also suggests the existence of exotic hadrons. These are other color neutral configurations like 4-quark states, here tetraquarks, molecule states. So this is 2 hadrons bind by the strong interaction. And then as QCD is also including gluonic degrees of freedom, one would also expect the existence of hybrid states and objects solely composed out of glue, which are referred to as glue balls. Candidates for all these forms of matters have been observed by previous experiments. However, the nature of these states is far from being understood. And I should also point out that candidates have been observed in the light quark as well as in the charm mass region. Yeah, so I think it's very fascinating that massless, the interaction of massless gauge bosons, the gluons can create heavy objects like glue balls, which have a mass of about 1700 MeV and upwards. But this is here the spectrum as predicted by recent lattice calculations. The lightest glue ball is believed to be a scalar at 1.7 GeV. The second lightest glue ball would be a tensor state at a mass of roughly 2.39 GeV, and then a pseudoscalar is followed at 2.56 GeV. So glue balls are believed to be produced in so-called gluon-rich environment and radiative J-psi decays with the annihilation of the charm and anti-charm quark in light mesons is such a glue-rich process. And yeah, large branching fractions in the order of 10 to the minus 3 and 10 to the minus 2 for the production of scalar or tensor glue balls have been recently predicted. So BESS3 is in a good position to have a look at these states, and yeah, candidates here for the scalar glue ball and tensor glue ball exist. In particular here for the scalar F0 1500 and 1710, which are close by in mass. And so it's not easy to map the observed states one-to-one to the predicted glue balls, because the pure glue balls can mix with nearby QQ bar states of the same quantum numbers to the observed meson resonances. So this is complicating the clear identification of glue balls in this mass range. So yeah, to access these states, BESS has carried out partial wave analysis of radiative J-psi decays into two pseudoscalars. We have investigated final states pi0, which is shown here, the invariant mass spectrum, eta, and more recently k short. So as you can see here, the decay dynamics are quite complex. So you have many broad and overlapping resonances, and the appearing resonances can couple to many channels. So the dynamical structure is here very complex, and usually the parameterization is quite challenging. Yeah, to approach this at BESS3, we performed model-independent partial wave analysis, where we do not parameterize the mass-dependent kinematics of the amplitudes, but instead bin our data in bins of the invariant mass and extract and fit our amplitudes to the data and extract the intensities for the contributing waves. So this has been done earlier for the pi0 system, and more recently for the k short system, which I will discuss now. So this is the result of the model-independent partial wave analysis. This is here the extracted intensity for the only contributing scalar wave in our data, and then for the tensor waves, we have you can develop the amplitudes by means of yeah, so these E1 and M2 transitions. Yeah, so you have two possibilities for a tensor wave, and yeah, the dominant E1 component features cleared in F2 prime 1525 in the extracted intensity. Moreover, we can also address the phases which are important to measure of the contributing 2++ waves with respect to the 1,0++ wave. This is shown here, independence of the mass. And yeah, as you can see, there are always two possible solutions marked in red and blue. This is due to some ambiguities in the amplitudes, which cannot be resolved with this model-independent approach. But if one requires continuation of the amplitudes from one data point to the next data point, this is naturally resolved. So we think that publication of this data is quite useful for future analysis, which could be coupled channel analysis, and so other authors can include our expected intensity and phases to their fits. So we as BEST3 have also performed a model-dependent partial wave analysis where we parameterize now our decay dynamics, and in our best fit, it's required that we have 7 scalar contributions and 4 tensor contributions in the K-short system. And for good fit quality, we also include a possible K-star and a K11217 in the K-short gamma component to reproduce the data by our fit very well. So, and as you can see here in this channel, the 1500 and the 1710 are both required. As I said, they are discussed to be linked to the glue ball ground state, and as well as a broad tensor state at 2.3 GeV is required in the fit. This is also discussed in the context of tensor glue balls. So then we have quite some time ago also analyzed eta, and as you can see by comparison with the K-short channel, there are striking similarities between the two channels. The F1500 and 1710 also appears here, and in both channels, the branching fraction of the 1710 is about 10 times larger than for the 1500. However, to draw further conclusion, a coupled channel analysis of these two final states, as well as including pi0, and other two pseudoscalar final states, would be desirable to describe all contributing resonances in one coherent approach with consistent parameters. So then we have also investigated radiative J-psi decays to phi-phi. Here you can see a dominant pseudoscalar contribution, which is rising at threshold. And in our fit, we also need a 2++ component at 2.3 GeV. And in the model-dependent fit, this component can be best described by including 3 F2 resonances with which have been previously observed in pi-nucleon scattering, and at least one of these states is also discussed to be a glue ball. So we revisited the phi-phi system in hadronic chi-sub-c decays, chi-sub-c 0, 1, and 2 into phi-phi and a recoiling eta meson. The chi-sub-c is produced from radiative psi-prime decays. You can see here very clear chi-sub-c signals, 0, 1, and 2, as an enhancement over backgrounds estimated from the sidebands. So we investigated the production of possible intermediate resonances in the phi-phi as well as in the phi-eta system. And as you can see, the data show no strong or significant deviation from phase-based distributions, which are shown here after simulating efficiencies from signal Monte Carlo, as shown in red. So yeah, statistics are quite low for this channel, but with more data currently recording, we definitely will revisit this channel as well. So if we move to radiative decays into 3-body systems, already BESS and BESS2, the old experiments, have investigated radiative decays into eta prime pi plus pi minus. And here they observed the X1835, and with larger statistics available at BESS3, we can confirm these observations. And along with this, there appear 2 new structures here at mass of roughly 2.1 and 2.3 GeV. Yeah, and the higher statistics allow us to investigate, to address further questions about the nature of the X1835. So meanwhile, we have shown that the quantum numbers of this state are consistent with pseudoscalar assignment. And we also discovered a new decay mode, K short eta. So here you can see a nice X1835 signal. So yeah, what is the nature of this X1835? It's still unclear. Interpretations include that this could be a glue ball, an antiproton-proton bound state, motivated by the proximity of the state to the respective threshold. And it's also suggested that this could be an excited eta meson. So to address these questions, we carried out further studies. We look for radiative decays of the X1835 into gamma phi. For the first time, we observe significant X1835. And in addition, also new in this mode is the eta 1475. For the X1835, the angular decay distributions are shown here, and they are compatible with 0- assignment. So this measurement suggests that the X1835 has a sizable SS bar component due to the production here of the phi in the radiative decay. And as a further check, we look for new production mechanisms. We exchange the radiative photon by an omega meson, which has the same quantum numbers, 1-, and look again here in the discovery mode, eta prime, pi plus, pi minus. And as you can see in the invariant mass distribution, there is no significant X1835 observed, and we place an upper limit for the production and decay of the X1835. So then, as I said, there appear two new structures in the larger data samples at 2.1 and 2.3 GeV. And to address these states, structures, we investigated radiative J-psi decays into K plus, K minus eta prime and K short eta prime as well. For the 2120, the lighter structure, we do not observe any significant enhancement, but there appears to be a broad enhancement above backgrounds in the region of the 2.3. And if we fit all three data samples together, we yield statistical significance of about 8 sigma for the production of an X2317 decaying into KK bar eta prime, and the extracted mass and width values are compatible with those observed in the discovery mode. So we also looked for possible decays of the 2317 into eta prime for the first time. And here statistics are even lower, and no significant signal is observed. So we place an upper limit for the decay of the X to eta prime at the level of 10 to the minus 5 to the minus 6. And if we combine this with the measurement in the KK eta prime channel, the experimental value is well above the limit. The experimental limit is well above predictions here, assuming that the 2317 could be a pseudoscalar glue ball. So in the same channel, eta prime radiative J-psi decays, we observed for the first time a very clear eta sub C signal here in both reconstructed eta prime decay modes. And we also place a measurement for the branching fractions here at a level of 10 to the minus 5. So this means we can also nicely investigate light hadron decays of conventional charmonium states. We have done this for eta C, and we can continue this for the H sub C. Our knowledge of this P-wave charmonium state is still quite sparse. We know that it undergoes radiative transitions to the ground state with a branching fraction of about 50%, and the rest of its decays is simply unknown. And therefore, this motivates the search to look for possible decays of the H sub C into light hadrons. At BESS3, we can access the H sub C via this isospin violating transition from side to S. we fully reconstruct our channels under consideration and look in the recoil mass of the pi0. So for the first 3 modes here, we observe a significant signal, place the branching fractions in the order of 10 to the minus 3. And for the last 2 decay modes, we only report upper limits. This has then been more recently extended to further channels and other charge combinations of the final states. And here, for the first time, we are able to observe H sub c decays into a pair of charged KNs and pi plus pi minus pi 0 with 6 sigma statistical significance. And then there is also evidence for some other decay modes. So if we now sum up all the known branching fractions into light hadrons, we yield about a branching fraction of 2%. So there is still room for further searches and exploration to understand H sub c decay modes. So then let's move up in energy beyond the open charm threshold. Let's leave the conventional charmonium states and turn to the new charmonium-like exotic states observed in this region. So there appear some charged charmonium-like states. And to be more precisely, it's isospin triplets. And BESS3 has established here 3 triplets at roughly 3.94 GeV, so the ZZ4020 and ZZ4030. All these states are seen in electron-positron annihilations into a hidden charm, J psi, psi prime, or H sub c with a recoiling pi-pi system. Then BESS has also investigated open charm final states with a recoiling pion, and it has been reported the 3885 in the D star channel here close to threshold, and in the D star bar with a recoiling pion again, the 4020-25. So then, yeah, the question is if these states here are related to the brothers or siblings of the hidden charm, of the structures observed in the hidden charm modes, and in general, for all these states, the nature is still unclear. So it's discussed that these states could be tetraquarks, or on the other end, hadronic molecules, or that they are even no resonances at all, that they are just due to threshold effects. And one further driving question is if strange partners of these states here exist, as suggested by the naive quark model. And to answer this question, BESS3 has carried out a study of electron-positron annihilation and investigated D sub S, D star with a recoiling K, and D sub S star, D0 with a recoiling K at center of mass energies above 4.6 GeV. The integrated luminosity of the analyzed data is 3.7 inverse femtobarn for all these energy points together. But the largest fraction of data was collected at one energy point, 4.681 GeV. And yeah, to be unbiased in our event selection and optimization of selection criteria, we blinded 2/3 of this large data sample. And after everything was understood concerning backgrounds and efficiencies, we unblinded the rest of the data. So we performed partial event reconstruction. We required one positively charged KN in the event, and on the other side, well reconstructed D sub S candidate in the K plus, K minus, pi minus mode, as well as in the K short K mode. Yeah, K short K. So you can see here very clear D sub S signals, and restricting our events to the signal region, we can now identify or go ahead and identify the signal in the recoil system. So if you look to E plus E minus annihilations, you have a recoiling KN, and on the other hand, on the other side of the event, there could be a D sub S and a D star. And both of these could stem from a hypothetical ZZS, which we are searching for. So you can infer the kinematics of the missing D star from the initial momentum and the measured momentum of the reconstructed particles. And the recoil mass is shown here and features a peak at the D star. However, the D sub S can also stem from D sub S, D sub S star decays into D sub S gamma or D sub S pi 0. And since we do not reconstruct here the gamma and pi 0, we would also accept these events in our selection procedure. So this has been simulated in Monte Carlo, and due to the kinematics of this decay process, it's also showing here a broad structure in our signal region. So we also accepted likewise these possible final states in our event selection. So now looking at the recoil mass of the Kn, we can identify the hypothetical ZZ in our events, and indeed at the data taken at 4.681 GeV, our large statistics data sample, we observe an enhancement close to the respective threshold over predicted backgrounds. So backgrounds have been estimated from control data samples and modeled in the fit2 data. And we performed a combined fit to all the 5 data samples and observe a significant enhancement at threshold here. The structure can be parameterized with the energy-dependent Wigner parameterization. We yield these mass and width values. So the width turns out to be quite small at about 13, 14 MeV. And yeah, if this okay, so the decay properties into D sub S and D star suggest that this new structure has a minimal quark content of CC bar and strange quark and an up or down, anti-up or anti-down quark. As already pointed out by the previous speaker, LHCb is seeing ZZS 1400 in its decay to J psi k, and the width is about 10 times larger than observed in this channel. So the question is, are these two structures somehow connected? Could they be partner states? And why is this one much broader than in this channel? So at best, we have also measured the cross sections. We expected the cross section at the high statistics point and place upper limits for the other energy points. So with this, I would like to conclude. BESS3 is successfully operating since 2008. We have collected large data samples in electron-positron annihilation and will do so for the next years. Electron-positron annihilation offers an excellent laboratory to study the spectrum of hadrons with low backgrounds. In that sense, we are also complementary to hadronic machines. I have presented recent achievements in the light quark sector, important measurements addressing conventional Schaumburnium states as well as exotic Schaumburnium. For this part of the physics program, you will hear more about in the following talk by Frank. And yeah, with this, I would like to conclude that studies in all of the discussed areas are ongoing and more exciting results still have to come. Thank you very much.
So thank you very much, Mark. This is a nice overview of on the Light Hadron section going on at BESS3. I see that Christoph has already raised his hand. So Christoph, please go ahead.
Hello, Mark. Thanks for the nice talk. This is Christoph Hannert from Jülich. Could you please go to page 21?
Mm-hmm.
I was a little puzzled because there on your page appears ZZ 4020, 4030, and 4025. Is it seriously thought that these are 3 distinct states as indicated by 3 different names, or is the option considered that these are the same guys?
It could be that they are the same guys, but first of all, yeah, one has to verify that they have the same quantum numbers, and yeah, and then probably what I think is missing is a combined fit to both of the channels, and see if that works out. Yeah, but so yeah, just from looking at the masses, the values would be consistent with each other's.
Well, actually, the Data group has combined the 4020 and the 4025 already.
Mm-hmm.
4030 I haven't yet thought about, simply because they are simply too close. Thank you.
Yeah. Mm-hmm.
Okay, very good. Are there further questions? Yes, Andre, please.
Actually, Eberhard Klemmt wanted to give some comment, but okay, he couldn't press. I think that he didn't understand what to press. Anyway, let me comment this thing. It was about, it's a really nice data about radiative decay, which you measured. They are really just beautiful. I mean, this, especially because you have pi, KK, and eta channels, and also omega phi and omega. And I must say that you correctly stated that it's needed combined analysis, and actually this analysis was done by our group, Von Gatchina group, and it was published about 1 month, I think, ago. And indeed, what is it's not only analysis of this data, but combined analysis together with elastic pi scattering and proton-to-proton annihilation at rest.
Yes. Yeah.
And actually what we see, it's really that we see some kind of signal. So if you, for example, just draw, you see not really one state, but you see the set of the scalar state, contrary to the tensor state, because in tensor case, we have a really huge peaks in the ground state for ground state. And then we have some small contributions, at least in the region of below 2 GeV. So that means that, of course, below 2 GeV, there is something, oh, sorry. Below 2 GeV, there is some contribution from something special, something different from tensor state. And this is difference from tensor state, of course, can come from the scalar global. Mm-hmm. And if you make what we made, we just try to measure intensity of the state, and then you indeed see that all the scalar state, they create some kind of intensity with a peaking in the region of 1850, and probably this with a width, let's say about 380 MeV, and possibly this is really signal of global what we see now. So this global really mixed with everything. And this is only explained why we see scalar state in this region. But for example, tensor state, which also can be produced in S-wave, it's not forbidden. They are not seen in this region. They are just dying very fast, as you expect for radial excitations. Okay, thank you.
Oh, thanks for your comment, yeah.
Good, I think we have to end the discussion here. Thank you again, Mark. And I would ask Andre and Christoph both to take down your hand. And then we now proceed to the next talk. Frank Nerling will talk on experimental results on charmonium-like states. So Frank, please, go ahead. Go to full screen mode if you can. Yep, fine.
Can you hear me?
Perfect.
Okay. Something once more. So you can see the slides?
You have kind of a strange mode that we can see not only your current slide, but also the future slide.
Ah, I see.
That's better.
Okay.
No, before was better.
Strange, 1 second.
I think you are switching to presenters mode, that's why.
Okay, so Let's see if it's working now.
Same thing. That's better.
Okay, once more, sorry.
No.
Not working.
You had the right format. Yeah, this is a correct format. So just don't touch anything. No.
Try Anzeige tauschen, Frank.
Anzeige tauschen?
Yeah, on top.
What about this?
That looks better.
Now you see the full screen mode?
Perfect.
Okay, very good. So, all this technique, we are getting more and more as the digital professionals. Oops. Okay. Yeah, okay. So let me start by thanking the organizers for the kind invitation to give here an overview on Chamonix-like states. I will restrict myself to the experimental review here. And as you see from my outline, after a brief introduction, I will also further focus and select the results to the plus and minus validation results. And here I will address all three types of the XYZ states, namely the Y, the ZZ, and then in the end, I will also come to the X states. And let me start showing you these two beautiful measurements of the Y4260 here on the left-hand side. I wanted also to maybe take this laser pointer. Yeah, now we have it on the left-hand side, decaying to J psi pi pi, and on the right-hand side here, the Z3900 decaying to J psi pi. Among others, the Y4260 is discussed to be a hybrid charmonium, but also a DD bar molecule, for example, whereas the ZZ is a manifestly exotic state and most presumably a 4-quark metastate. I will come back to that. However, as mentioned earlier, both are also discussed to merely be a threshold enhancement, so the nature still needs to be understood. It was indeed the discovery of the J psi in 1974 that started investigations of the charmonium region, where bound charmonium states can successfully be described using powerful potential models. What I'm showing you here is a so-called level scheme where the states are ordered along the y-axis according to their mass and along the x-axis according to the quantum numbers. And indeed, before 2003, in particular, beneath the open charm threshold, there is excellent agreement that we find between theory and experiment. All the predicted states have been observed with the properties as expected. However, above the open charm threshold, there are many unexpected states that have been observed since 2003 that do not fit the expected pattern. And they can be grouped into these three groups once more. Here, the so-called Y states, the supernumerary vector Y states, where the Y4260 is one famous example. And here, the charged Z states, where the ZZ1300 is rather well known. And thirdly, here also the X states, where the X3872, meanwhile, renamed according to the new PDG naming scheme to the Chi sub C1 3872, which was indeed the first of the XYZ states observed back in 2003. And to have these unexpected findings is not really a big surprise, because if I may remind you, whereas in the simple quark model on which the potential models are based on, mesons are described as color neutral Kukuba pairs. Q3 not only allows for, but even predicts exotic meson states beyond the simple quark-antiquark picture. And commonly discussed are so-called hybrid mesons. So I have a cuckoo bar meson here with some additional gluonic degree of freedom, or so-called tetraquarks consisting of 2 quarks and 2 antiquarks, or so-called glue balls entirely consisting of glue. And given, especially here for the XYZ states, I would like to introduce a few further 4-quark configurations discussed and proposed, namely molecular states, which are loosely bound systems of 2-quark antiquark pairs, or the so-called heteroquarkonium, where you have a heavy quark antiquark core surrounded by a light quark antiquark pair, or the so-called diquarkonium. And here I show you an overview of the relevant +/- experiments that have contributed during the last 2 decades to our field of the exotic XYZ states. And first of all, to mention here the CLIO and the upgraded version, the CLIO-C experiment at Cornell University at the Cornell Electron Storage Ring. It was run for more than 2 decades and reached center of mass energies of up to 12 GeV. Then secondly, let me mention the Barbar experiment here, also in the US at SLAC, and that took data for 1 decade nearly, and this was running mostly or most of the time to a large extent at the ε4s energy of 10.58 GeV, and has collected an integrated luminosity of more than 500 inverse femtobarn. Then of course the Bell experiment here in Japan at Keck B in Tsukuba. The machine has been upgraded to Super Keck B, and there's also now an upgraded version of the detector, the Bell 2 experiment. Bell took data also for a decade, similarly as Barbar here at the ε4s energy mainly. It has collected a luminosity twice as large as the data sets collected by Barbar. And now we are very much looking forward, of course, to the Bell 2 experiment that started. We heard a nice talk today. So commissioning is done or partly ongoing still, and we are looking forward to the first physics result based on, in the end, that is the plan to have 50 times the statistics that Bell has collected. Last but not least, let me, of course, not forget to mention BESS3. BESS3 in its upgraded version is taking data since 2008. It is dedicated to the Charmonium region indeed. So we are able to get center of mass energies of up to 4.6 GeV, and now after the recent machine upgrade, even going close to 5 GeV. And yeah, as you will see, there are also impressive results coming from that experiment. Yeah, and the +/- experiments offer various ways to produce and to study the XYZ states. So first of all, we have the direct formation here, where the plus and the minus beams collide, and via a virtual photon and a vector dominance model, our hadronic outgoing system is produced. In this case, the spin quantum numbers are limited by the photon acting as a spin filter to 1-. But you could also have an additional recoil particle, and then you can also reach other quantum numbers. If your center of mass energy is that high, then you can make use of the anyhow taking place initial state radiation mechanisms, and then you can reach lower energies. Of course, you can also imagine to not just produce 1 Charmonium state here, but 2, and that would be the double Charmonium production. Of course, you would need sufficient center of mass energy to produce 2 Charmonium states. And then, of course, there are, for the B factories who are producing B mesons at very high statistics. Here we have the B meson decays, in which Charmonium states are produced and can be studied at B factories. Then let me mention also the 2 photon production process. This is a complementary production. It's highly suppressed due to the 2 partly virtual photons here exchanged. And then you have in a central production kind of scheme here, the hadrons being produced. And indeed, in my talk here in 25 minutes, given this huge variety of results, I need to restrict myself, and I will focus on the E+/- annihilation production with and without applying the ISR technique, and the results from B meson decays. Yeah, and then let's come to the results, and let me start with the vector Y states, and let me start by recalling some interesting history. So the unexpected vector Y states, the Y4260 on the left-hand side and the Y4360 on the right-hand side, had been observed by Barbar, both using the ISR process, and I show you here the corresponding observation plots. Both observations were immediately confirmed by Cleo and also by Bell in the same process, namely decaying to J psi pi pi here on the left-hand side for the Y4260 and to psi to S pi pi for the Y4360 on the right-hand side. And now let's have a look to the latest BEST3 results on both here. On the left, the J psi pi pi direct production, and on the right-hand side, the psi to S pi pi production. And what I show you is the measured Born cross-section that we here on the left for J psi pi pi find inconsistent with just a single resonance of the Y4260. So we need to accommodate a second structure here in order to describe the data, and this is asked for by high significance. Observing here is the Y4260 much more narrow and at a slightly lower mass of 4.22 GeV, plus a second structure here visible as a shoulder in this plot, which is the Y4360 that we observe here for the first time decaying to J psi pi pi. And on the right-hand side, I show you here the psi to S pi pi cross-section, which also shows indeed two structures here, two peaks. And those are also consistent with the Y4220 here and the Y4390 as we observe them in the J psi pi pi channel. And indeed, we also observe these two structures consistently also decaying to H sub C pi pi. And let me come back to that on this slide, where I would like at this point to briefly summarize what happened to the Y state. So thanks to the unprecedented high statistics we have collected with BEST3, now we resolve two structures consistently here, not only in the J psi pi pi production and the psi to S pi pi production, but also in the H sub C pi pi final state. So it seems that the original Y4260 is now rather a Y4220 and the Y4360 is rather a Y4390. At least this is as we see them in the BEST3 data. Yeah, and then not to forget, they are also both meanwhile consistently observed in the BEST3 data for the first time in open charm decays, namely in the plus and minus going to the 0, d star minus pi plus. And here again, we see these two structures here, and the two resonances are needed by the data with a significance of more than 10.5 sigma. The lower mass one here is consistent with in terms of the resonance parameters as in the other final states I just discussed before, whereas this state here, or this peak here at a higher mass at 4.4 GeV seems to be a combination of the psi 40-40-15 and the Y4390. It's a little bit more complicated, and some further more sophisticated analysis is needed here. But to conclude, we have now the first Y decays seen to open charm, and we find consistently the structures as in the other final states of J psi, H sub C, and psi to S pi pi. Yeah, and after this major step forward, let me come to a selection of further decay modes of the Y4260. And a recent new BEST3 result is on the decay to J psi eta. So what was done here, what we did is a simultaneous fit to two data sets, the high statistics XYZ data here in the top and the lower statistics scan data here in the lower plot. And what we did is we assumed the psi 40-40 here and fixed the parameters to the PDG values. And what we find then here are these two structures, and again, consistent with the Y4220 and the Y4390 as we observed them in the other systems discussed before. In the same paper, there's also this compilation plot of the masses, the width versus masses values from the various measurements here from the BEST3 data, and also comparison for the Y4360 by the PDG. And it seems that there is nice clustering here, whereas for the high mass case here, the width now seems to scatter more than the mass at this moment. And also the production cross-section for E plus E minus J psi eta prime has been measured by BESS here. Again, the simultaneous maximum likelihood fit has been performed. However, here two different decay modes of the eta prime. And on the right-hand side, you see the measured cross-section, which we first try to describe by a single psi 4160 on the one hand, or a single Y4260 on the other hand. However, the data ask here for a coherent sum of the both of the resonances. So both states are asked for by the data with a rather high significance of 4.0 and 6.3 sigma respectively. So the cross-section, by the way, is an order of magnitude smaller than the one of the J psi eta. Of course, it would be great to repeat this analysis with more statistics. And in the end, it will also help to understand and to study eta prime mixing. Okay, and another brand new result has been published by BESS3 recently. Here we performed a simultaneous fit of the eta C pi plus pi minus pi 0 cross-section to 16 different hadronic decay channels of the eta sub C, and measured by that the energy-dependent bond cross-section at 6 different center of mass energies between 4.18 and 4.6 GeV. And this is here on the right-hand side how it looks like. And what we find is that the cross-section is consistent here with the production via Y state. So there's a clear evidence here now, the first for the Y4220 decaying to eta C pi plus pi minus pi 0. And BESS3 is also constantly addressing further possible decay channels of the Y states into just light hadrons only. And I show you here a compilation of some of our recent results here for the light hadron decays, of which 2 are brand new, namely the ones here on the left, the PP bar eta and the PP bar omega. And still, as you see, so there's no clear evidence for such a decay that we are finding. Interestingly, the Y4260 is also still not observed in B decays. So Bell has recently searched for it in B plus as well as in B0 decays for the Y4260 in its decay to J psi pi pi. However, they do not find significant evidence and just provide 90% confidence level upper limits instead of 1.4 and 1.7 times 10 to the minus 5 respectively. And this is really interesting. So it seems that we have different states produced and observed in E plus E minus production as compared to B decays. I mean, you see the X going to the same final state, which was used here also as a control sample, is existing there in the B decays, but not the Y4260 going to the same final state. Okay, last but not least, let me come back to the Psi2S pi pi system. So the plot here on the right, you remember, this is from BESS3, in which we now resolve also these 2 Y states, Y4260 and Y4360. And on the left, I show here the original confirmation plot by Bell of the Y4360 here, that was initially reported by Barbar, in which, however, they also observed the second state here, the Y4660, with a significance of larger than 5 sigma. And indeed, Barbar later confirmed the state, whereas, however, Bell also observed the Y4660 here in further decays like lambda C, or D sub S1, and D sub S star. So, and it would be, of course, great to have as a Y4660 also confirmed by other experiments and in these further decay channels. Okay, then let's move to the ZZ states, which in a sense are the most interesting one. And let me start here with the first of the ZZ states, the Z4430 here as observed by Bell in B decays, decaying to psi prime pi. It is a relatively narrow state here, observed with a significance of 6.5 sigma, and it is charged. And this, so this in combination, the mass here above for GeV in combination with being charged makes it a manifestly exotic state. Why? Because the minimal quark content should be something like CC bar UD bar. And then it would be a 4 quark or even further or more quark states, and thus a manifestly exotic state. Barbar searched for it, however, does not confirm it. LHCb finally confirmed it, including the spin parity that were firstly already constrained by Bell to be 1+. And Bell reported it also in a different decay, namely also to J psi pi in B decays. And this again was not confirmed by Barbar. And otherwise, there are two more charged ZZ states reported by BES3 and partly confirmed by Bell, namely the ZZ3900 and the ZZ4020 here. On the left decaying to J psi pi, on the right the ZZ4020 here decaying to H sub C pi. And here indeed you see two plots for each of them. Those are the second one, the right ones are the neutral partner states that have been found, establishing here these two isospin triplets. Both states were additionally also observed in open charm decays, and that these are the same states observed in different decays is meanwhile, at least for the ZZ1300, proven by an amplitude analysis. And nevertheless, despite this great success, there are still open questions. So what is finally the nature of these ZZ states? And of course, it is important to also explore further decay channels and search for them. Yeah, and already some while ago, it was Bell who reported two further charged ZZ states, namely the ZZ4050 and the ZZ4250 decaying to chi sub C1 pi. And they performed a Dalitz plot analysis, and I show here in the top plot the chi sub C1 as observed and reconstructed in its decay to J psi gamma. And then the lower plot here shows you the Dulles plot fit results, where the red histogram here is a solution with the two ZZ states included and the blue one here without. So interestingly, okay, of course, this is also, these are also manifestly exotic states because they are charged. And Barbar, interestingly, does not confirm them. I mean, they are not really excluding them. I mean, they did some further, more sophisticated study modeling the chi-pi resonance structures here, but still have 1 to 2 sigma significance only. So maybe more statistics would help here. BES3 does not see the ZZ4050 here to psi 3770 pi. So, and then, so there's no confirmation yet. Also, we do not know yet anything on the quantum numbers. And it would, of course, be worth to search for the neutral partners decaying to chi sub C1 pi 0. Okay, and then there is yet another Z state reported by Bell, and this, which has not yet been confirmed, namely the ZZ4200. It was observed and reported in 2014 in the decay to J psi pi with a significance of 6.2 sigma here. In the same analysis, also some evidence for the ZZ4030 here decaying to J psi pi was found. And also the quantum numbers were studied, and the 1+ spin parity assignment is preferred over other hypotheses from the Bell data. However, also this state here needs independent confirmation, and especially also it's worth to search for a neutral partner state decaying to J psi pi 0. Yeah, and coming to the end of the ZZ part, let me at least briefly mention a very important recent results that was already discussed in detail in the previous talk by my BES3 colleague, Mark Paliseus. I mean, given this beautifully established isospin triplet ZZ3900, it is natural to also expect a strange partner state. And we searched for such a state here in the new BES3 data and found ZZCS 3985 candidate here in the open charm decay to D sub S D star or respectively D star sub SD, in which we observe it here in form of these relative narrow threshold enhancement with statistical significance of 5.3 sigma. And this is the plot. I mean, this is here the recoil, the K-on recoil spectrum. And interestingly, and we heard this this morning also, LHCb is reporting that that sub-CS candidates, one here at 4 GeV and one at 4.2 GeV, even in B going to phi J psi K. And the question, of course, is whether these observations of the same state observed not only at 2 different experiments, but then also in 2 different decays, namely LHCb in the hidden charm and with BES3 here presently in the open charm channel. Yeah, so I do not have time to just discuss that in detail, but that was done by Mark already. And now I move to the third topic I want to cover in my talk, namely the X-states.
Frank, excuse me, you're entering overtime now.
Okay, I can be very short here because this was discussed already. It's clear that here, for the nature of the X, we need the line shape to be understood precisely, and Panda is a very promising upcoming experiment who will be able to do that. And then it's interesting that we also observe the X in radiative decays. That was done already previously, and now also with BES3, we see it here in the J psi pi pi radiative decay as well as omega J psi on the right-hand side. And what we did with a few center of mass energy points is to measure the cross-section. Of course, this is limited here in the data points, but from this first glimpse, we find the shape here consistent with the production via a Y4260 state. And just for completeness also on the radiative decays here, on the right-hand side, I show you a recent Bell result for the radiative decays of the X in B decays, namely on J psi gamma here with 5.5 sigma significance observed, and then an upper limit, so no signal here for the psi to S gamma, which is interesting since Babar reported evidence for both cases. And with BES3, we indeed confirm now the Bell result of having an observation for the gamma J psi, but not for the psi prime gamma. And if you look at this, it's interesting. So we have a group of BES3 and Bell, where the data is more in favor of a molecular state, looking at this ratio of the branching fraction, whereas this Babar and LHCb, who are more in favor of a tetraquark interpretation. And indeed, in that same paper, we studied also the open charm decays, and those are important, as we know, and even dominating. And this decay has now also been observed by BES3 with 7.4 sigmas here. There's no evidence, on the other hand, for the decay to gamma D plus D minus, but the open charm decay is indeed also found to be dominant with about a factor of 10 as compared to J psi pi pi. So this result will probably further help to understand the nature of this state. For completeness, I wanted to have this slide on the X3915 in B decays. This was seen decaying to J psi omega by Babar also. And then it was even by Bell and Babar also seen the 2-photon production modus. And now, interestingly, the BES3 has explored now also another decay channel, the chi sub C1 pi 0, where we observe the X decaying to with a high significance of more than 5 sigma, whereas the recent Bell result now searched also for that decay and for both, for the X3872 and the X3915, but there is no evidence in their data. So again, also for the X states, it's interesting that we have obviously different states observed and produced in E plus E minus production as compared to B decays. And this brings me to my summary and some perspectives. I hope I was able to summarize here this nice new era of germanium-like states, more than 20 unexpected states in the germanium region. I discussed the famous and recent results on the supernumerary vector Y states, as well as on the charged Z sub Z states, and also on the X. And as an outlook, I mean, the B factories, Clio and Babar, have run for 1 and 2 decades. They are done now. Bell also run for a decade, and meanwhile is upgraded to Bell 2. We are looking very much forward to new results here. And BES3 is successfully operating since 2008 with unique possibilities to explore the XYZ states. The machine upgrades allows us now also to go to studying states up to 5 GeV. And for the upcoming and future experiments, I would like to mention Panda as a complementary and unique proton-antiproton experiment, and of course the super tau charm factory in China, Russia. So this will all help us to further complete the exotic multiplets. What is needed, as we saw, high statistics and precision, and it is very useful to have these states, these new exotic states being observed and confirmed with different probes. Thank you very much for your attention.
So thank you very much, Frank, for this nice overview of what's going on in the field. This talk is open for questions. Please raise your hand if you have a comment. Seems to be relatively clear to people.
Well, I could maybe say something from my side regarding the question by Christoph. He was asking the question to Mark about this other state, which he called Z sub C 4030. And indeed, I mean, we have here a candidate which we observe decaying to psi to S pi, but this is a rather complicated situation still, because it is changing a lot how it looks like in the different set of mass energies. And therefore, I would not consider that yet as an established isospin triplet.
Good, thank you for answering that comment posed before. If there are no more questions, no questions, then I would like to thank you again, Frank. And then I think we should continue, maybe catch up 1-2 minutes. So Christoph, you're the next speaker. So Frank just passed on the word to you. So please go ahead.
Okay, thank you very much. But I will have to wait until Frank stops sharing the screen. But I can already thank for the opportunity for giving this talk. Okay, here we go. Okay, what I will be talking about is unconventional meson states, and I extended the title a little bit, so that I will only focus on 2 and more heavy quarks. Therefore, exotic states with single heavy quarks will not be part of this presentation. And since this is the first theory talk in this context, I should mention that there are many recent review articles on the subject. These first 6 ones here, starting in 2016, and the last one was ours last year. They are rather general reviews talking about the various different aspects of the XYZ states, while there's a dedicated review on molecules appearing in 2018, which I would recommend if you're interested in that subject. A picture like this you've seen before in various talks, so I can be rather brief on the introduction here. The important point is that all exotic candidates appear above the open flavor thresholds. Many, but not all states appear near S-phase thresholds of narrow states. One candidate who doesn't appear close to a threshold is, for instance, ZC 4430, which is sort of a standalone thing here, no nearby threshold, but there are other examples. This picture, by the way, is from our 2018 review. Therefore, in the meantime, more states appeared, but I think this plot here is already impressively full. Another important aspect is that states are not all not near all those S-phase thresholds. Therefore, not all states are near thresholds, and not all near all thresholds are states. Then there are hard states, which were mentioned in a couple of the previous talks. Therefore, those are definitely containing at least 4 quarks. And another important feature is that the lightest negative parity exotic, the 4260, or maybe I should now call it 4220, is significantly heavier than the lightest positive parity exotics, which are the 3872 and the ZC 3900. What I will run you through now in this in the first part of this talk is the various different interpretations of those structures. They were all mentioned already. Therefore, the 2 compact versions are tetraquark and heteroquarkonium. And then there is an extended version of interpretation, which is called exotic molecule. And really this extended versus compact will at the end of the day be the decisive feature. So what I will do now in this talk is to review the ideas behind and also to tell you something about how to disentangle from experiment these three different possible structures here. Well, let me start with the heavy tetraquark. Actually, this is, as mentioned, a straightforward extension of the original quark model. Already in his famous quark model paper, Gell-Mann pointed out that there should be more complicated structures. So for instance, for mesons like QQS, QQ bar, there should be states like Q bar, QQ, and so on. Therefore, the picture underlying is really a diquark, anti-diquark picture, which was originally proposed by Bob Jaffe in the light quark sector already in 1977, and was picked up by Mayani et al. In 2005 to extend it to systems with a heavy quark and a heavy anti-quark. The idea nowadays is, now what I tell you about is the current status of these kinds of studies. There was a lot of history behind. But the current understanding, especially pushed by the Rome group, is that one has some sort of potential, well, as indicated here, one diquark sitting on the one side, the anti-diquark on the other, and spin-spin interactions only occur within the diquarks. And the separation here takes care that the crosstalk for spin interactions is absent. Moreover, it was recently argued by Ali et al. In 2018 that one needs a tensor force to properly account for the spectrum, and in particular to avoid the appearance of a somewhat unphysically light 3 state, which was already pointed out by us a few years earlier. Therefore, in total, now the effective Hamiltonian consists of these terms here. There's an L² term, which allows one to distinguish terms of higher angular momentum from the S-wave states. There is an LS term. This is a spin-spin interaction just within the diquarks, and here is the tensor force. As an example, let me show you what one gets, for instance, for the negative parity states. Therefore, besides now the vector states that need to be adjusted to the data, therefore, here, for instance, one needs the two states in the 4260 mass range that were stressed in the previous talk by Frank. That one has a 4220 and a 4390 around. And also what is used in this fit that this shoulder here is explained as a 4330. Whether these states all survive the further experimental studies remains to be seen, but the model is quite flexible. But what one certainly needs here is 4 states in the 1-, and regarding where they are located, other states are predicted now for different quantum numbers, amongst them even exotic states. Clearly, at the moment, there are many more states predicted than observed. This could be 2 possible reasons. One is that the diquark picture is too restrictive. For instance, Richard et al. Already pointed out some 4 years ago that one should not only include the color 3 bar diquarks, but also the color 6. Another possible explanation is that there are simply more states in the peaks than currently assumed. One example could be here that the Y4260 in reality is not a single state, but 2, and something similar could happen for other states. Therefore, in this reference here, you find a discussion of possibly 2 states underlying the structure called X3872. This could possibly be resolved by the high resolution measurements that will become possible at Panda, as mentioned by Frank in the previous talk. A very interesting theoretical thing that I would not want to leave unmentioned is tetraquarks containing 2 heavy quarks and 2 light antiquarks. So those were predicted with very different approaches, say QCD sum rules, lattice QCD, and also phenomenology. These studies already started in the 1980s. And from the Eichten and Quick picture paper, one can pick up a very nice physically intuitive explanation why one should expect those things to exist. Namely, there's something which is called heavy quark diquark symmetry, because if we put the 2 heavy quarks very close together in space, they form really a color 3 bar, as mentioned before, and the color 3 bar behaves the same way as an antiquark. Therefore, what should be the case is that the mass difference between QQ, Q bar versus QQQ heavy light, should be of the same range as a heavy antiquark, two light antiquarks, and a minus a heavy antiquark and a quark. The right-hand side is very well known because this is just the mass of the singly heavy baryons, because antibaryons have the same mass. So this is a regular singly heavy meson. And with the discovery of the doubly charmed heavy baryons, one can make a prediction for these states, which turn out, however, that in the charm sector, these doubly heavy tetraquarks are not bound. However, if one uses a similar approach that nicely predicted these doubly charmed states, one can also go to the double B sector, and then indeed those states turn out to be bound. I show you results on the next slide, theoretical results. Actually, what this here is, the assumption is really what you need to assume, I must say, is that there is this heavy quark diquark symmetry at work. At the end of the day, if you think about it, it's basically an expansion in the size of the QQ pair versus the size of the light quark cloud. And this, in fact, is an expansion in lambda QCD over MQ times the velocity. That's the typical momentum of the heavy quarks. So whether or not this expansion is really operative remains to be seen once we have data, which we so far don't have. But what is found in all theoretical studies, and I will show you details on the next slide, is that in the 1+ channel, there should be bound states, but the predictions are not very consistent. Therefore, what you see here in green are the predictions from phenomenological models. They all agree that bound states emerge, but as you can see, the bound state energies actually scatter over the map. Then in this column, what you see is lattice QCD using static potentials. So here the potentials are derived really from static B quarks, and then one uses that in a similar way as the Born-Oppenheimer approximation for molecules to calculate the bound state energies. So these are typically bound by some 50 MeV. And here the heavy B quark is treated with NRQCD methods, and then the binding somewhat goes up. Therefore, as you can see from the discrepancy between these two kinds of studies here, you can see that the lattice systematics needs to be somewhat better understood in order to bring these results in consistency. Maybe some systematics were underestimated, but what we can say is one should expect indeed that in this heavy quark-quark, light antiquark system, in the BB system, there should be states. And there's an interesting proposal by Tim Gershon and collaborators that maybe displaced BC vertices will allow one to eventually measure states like this at LHCb. So that would be great indeed. Okay. Let me come to the hydrogermanium picture. As mentioned in a couple of the previous talks, this assumes that there is a very compact heavy quark antiquark core with a light quark surrounding it. And this picture emerged after the observation of the Y4260 in the J-psi-pi final state, but not in DD bar, as one would have expected for a quark model state. And accordingly, Misha Voloshin proposed or speculated that the reason for this kind of decay pattern is that there is a J-psi core or a heavy vector core surrounded by like a light quark cloud. Heavy quark spin symmetry, however, predicts that if there is a pure spin 1 heavy quark antiquark core, this should be preserved. This spin 1 should be preserved into decay, as it is the case in J-psi-pi. However, the Y4260, as you've seen in the previous talks, is also seen in HC-pi final states. And the explanation that Lee and Voloshin then came up a few years later was that Y4260 and Y4360 are actually a mixture of two states with the spin 0 and the spin 1 core. And this mixture then allows for an explanation of the HC-pi data. The nice thing is, however, that if we know the mixing between Y4360 and Y4260, one can actually look for the spin star partner states, because heavy quark spin symmetry also says that if we replace the core by its spin partner, but leave the light meson cloud unchanged, the states that emerge should have the same properties, simply because the heavy quark spin decouples from the system. Therefore, we can, in the 1 case, we can replace the 1 state, which would either be J psi or psi prime, by the spin partner states. It's an eta C or an eta C prime. And here the core would be the HC, and the 3 spin partner states for the HC are chi C naught, chi C1, and chi C2. And the spectrum that emerges once one does that is this one here. Therefore, in particular, one predicts a rather light 0- state, which is 100 MeV below the Y4260. And the important point to stress here is that the mixing that emerges violates spin symmetry. Therefore, what is really the interesting pattern to be observed is not necessarily the spin symmetry conservation, but the amount of spin symmetry violation. And this will be a theme that comes back in the next part of the talk. Okay, hadronic molecules. Hadronic molecules is sort of my favorite kind of picture here. These are few hadron-bound states bound by the strong force, and we know that they exist simply because the light baryons, proton and neutron, form nuclei. And if you also allow for strangeness, you even get the hypertriton as a lambda d-bound state. And the properties are can therefore typically be read off from the properties of the nuclei. Bound states, the binding energies are typically very small. For the deuteron, it's 2.2 MeV, which you can calculate from that a binding momentum of some 40 MeV. And the hypertriton has 130 keV. Therefore, that's really very little, of the same order of what is currently expected or experimentally found for the X3872, which would correspond to a binding momentum of the order of 30 MeV. Weinberg already proposed in the 60s how to quantify the molecular component of the state, because he showed that the residue at the pole can be directly related up to kinematic factors that are calculable to 1 - lambda square, where 1 - lambda square is the probability to find the molecular component in the bound state wave function. And these quantities also directly relate to scattering length and effective range in the corresponding channel. Therefore, the question is not, are there hadronic molecules, because nuclei exist, but the question to be addressed is, are there mesonic molecules? And I only have the time to start to discuss these things very generally. But already there we find some non-trivial pictures. First of all, the constituents for hadronic molecules must be narrow, simply because if the states are broad, like the D0 to 2400 or the D1 to 2430, the width is 300 MeV. Therefore, these guys will have decayed already before they have time to form a hadronic molecule. Therefore, the constituents at our disposal are, first of all, the ground state, single heavy states like the D0, the ground state D, which is the 0- state, and the ground state D star, which is the 1-. And then as the leading positive parity states, that's the D1, which is a 1+, and the D2, which is a 2+. Both have widths of the order of 30 to 50 MeV. Since the strongest attraction is expected in the S waves, this thick solid line here indicates where we should expect, above which line we should expect these exotics. And indeed, what you see is typically all the candidates for exotic states are above this thick line. Moreover, this simple picture already nicely predicts, that the Y4260 is as much about 400 MeV heavier than the X3872, because in this molecular picture, this mass difference here can be related to the mass difference of the D1 and the D star, although these numbers should be taken very grossly, because obviously binding forces also change them when you do molecular detailed models, will change the exact numbers, but the order of magnitude is actually intriguing here. Moreover, in this picture, to come to the lightest 0- state, we need to combine the D1 we need to combine a D2, sorry, a D1 with a D star, because otherwise we don't get a D minus in an S wave. Therefore, the lightest 0- state is expected up here, which is about 100 MeV above the mass of the Y4260. And remember, in the hydrogermanium picture, we had something like 100 MeV below the Y4260. The important point to mention again is what drives these differences, again, is spin symmetry violation, because the mass shifts here are driven by the mass difference between D and D star and D1 and D2. And these mass differences are again driven by spin symmetry violation. Therefore, again, the amount of spin symmetry violation is sort of the magnifying class for the structure underlying the certain states. Therefore, I don't want to now go into details on how to model these states, because there will also be a talk, for instance, by Vadim Baru later in this conference, where he will tell you how to describe the pentaquark states in the molecular picture. What I want to do here is I want to give you a model independent criterion for virtual states and resonance, and that I will then apply in the remaining minutes for the double J psi structures. Before I do that, however, let me remind you of the notion of bound states, virtual states, and resonances. What you see here is the corresponding pole locations in the so-called momentum plane, in the K plane. What you are probably more used to is the S plane, which is covariant, but the K plane is completely analogous. There's only the advantage that in the single channel case, it doesn't have a cut. Then abound the upper half plane here is in K the physical A plane. The lower half plane is the unphysical plane, or the so-called second sheet. In the first plane, poles, or the first sheet, poles are only allowed on the imaginary K axis. In the second sheet, poles are allowed either single poles on the imaginary negative axis, or if you have a resonance pole somewhere in the plane, here there must be a mirror state, mirror reflected on the imaginary axis. Also here, this is just a consequence of the Schwarz reflection principle. Now, near threshold amplitudes can always be described by the so-called effective range expansion already introduced by Bethe in the 30s, if I recall correctly. So this is how one writes it in terms of A and R. And from this form, one can easily read off the location of the poles in the momentum plane. And as you can see, the different poles that appear actually are driven basically by the ratio R over A. Okay. If I now look at the locations of the poles in the plane of scattering length versus effective range, this you see here, bound states in the sign convention we are using have negative scattering length, and R can be either positive or negative. I should mention that two large positive effective ranges are forbidden by the Wigner bound. Virtual states sit up here, resonances sit down here. Therefore, we can now generalize the Weinberg analysis. Let's assume we have an attractive interaction. Then for a bound state, the scattering length is smaller than 0. If there is no bound state, but an attractive interaction, the scattering length is larger than 0. Then Weinberg locates a molecular state here. It has a large scattering length and a small, typically positive effective range, while compact states are located down here. They have a small scattering length and a large negative effective range. Therefore, what happens if R changes sign? Therefore, if we basically make the interaction somewhat weaker in order to move away from the bound state region, well, then for the molecule, what happens is A changes sign by going through infinity. Therefore, the molecular state disappears here and appears here as virtual state. So that's a straightforward analytic continuation. While a compact state has no choice but to move this way. So it appears as a typically narrow resonance above threshold. And what we've demonstrated in this paper up here is that these features can be nicely combined into a single compositeness measure, which again is described solely in terms of the ratio of scattering length and effective range. There are also other approaches that come to a somewhat different extension away from the bound states, but this is the quantity I want to use. And the following. In order to apply this, let's look at the double J psi spectrum that was talked about in Xang Xing's talk about the LHCb data. And here is the data together with the LHCb fit containing the interference. And if I want to say contrast compact states versus molecules, I first have to ask what thresholds are around. And as you can see, there are many thresholds around. Therefore, in order to proceed, we make first a simplifying assumption, namely, we only look at the vector-vector channels in the same mass range, and that allows me to just include in the analysis the double J psi channel, J psi psi prime, and the J psi psi 3770. And then we performed two kind of analyses. One is a 2-channel fit, and one is a 3-channel fit. In the 2-channel fit, we in addition include the psi prime J psi threshold, and here also this 3770 threshold is included as well. It turns out in order to get away with a 2-channel fit, we need to include some energy dependence in the potential, while in the 3-channel fit, we can get away without it. And as you see in both cases, we get an excellent description of the data. If we ask now where are the poles located in the analysis, one finds that in the 2-channel fit, there are poles somewhere in the complex plane. One finds 2 additional poles, one up here above the threshold, one somewhere in the complex plane, all not very closely constrained by the data. But in any case, we need here a state very close to the J psi threshold. If we take into account the 3-channel fit, we only need 1 additional pole to, in addition to just the J psi structure at threshold, but this pole is even more badly determined. Therefore, from our analysis, this follows that the interesting structures is not around 6.9 here, but actually at the J psi threshold. So let's have a closer look at the J psi structure. What one finds is, comparing the different fits, we find 2 different fits in the 3-channel model, that in the 3-channel model, this state predicted at the J psi threshold is by far predominantly molecular, while in the 2-channel fit, the data is consistent with both, either being the state being molecular or having a large compact component. But the nice thing is, what we can also show is that the different approaches give very different predictions in the J psi prime cross section. Therefore, once this will be measured, our scenario, one of the scenarios we propose could be either validated or both could be falsified. Therefore, this brings me to the summary. Therefore, we saw that multi-quark states reflect their structure in the line shapes. What is in particular very important is the amount of symmetry violations. What I focused on here is the violation of spin symmetry, but obviously also the SU3 flavor structure is very interesting to look at, because also that contains a lot of non-trivial information on the underlying structure. What we clearly need is better data and more theory studies, but we are in very exciting times for these exotic studies. Thank you very much for your attention.
So thank you, Christoph, for this nice presentation here. We already have a couple of hands up. I think Adam was first with his hand up, so please go ahead.
Hi, Christoph, and thank you for the very nice overview. You mentioned that, well, that's clearly expected, I would say, that, you know, when you have say wide states, so wide constituents, they would not form a molecule. But is there a quantitative argument at what scales does this happen?
Well, I presented the theoretical papers for that rather at the beginning here. For instance, when you look at this paper here, then you will see there are different results shown for the investigation of the broad D0 state together with D bar, just looking at what happens. And when you, as soon as you switch on, this is really a Fadeev calculation, as soon as you switch on the width of the D0, you see that the signal in the data completely is washed out simply because the emerging molecular state is at least as broad as a constituent, and in this calculation it turns out to be even broader. Therefore, the 300 MeV completely kill any signal. In the Gu et al. Paper here, that's I think Gu et Meissen, if I recall correctly, the argument is more presented with respect to the time scales. I cannot remember anymore, however, how quantitative this investigation is made here. You have to look it up. But here you can really see what happens if one switches on the various components in the calculation, and that at the end of the day, if really the width and the three-body cuts are properly included, the signal is gone.
Thanks.
Welcome.
So let's proceed to Akira.
Okay, thank you very much for a nice review. And would you please go to page 13?
Sure.
Where you discussed that in the case of molecule, then the bound state goes to virtual state. Then I agree for S-wave, but my point is that when we change the strengths of interaction smoothly, then the A is does not move continuously from negative to positive, but the 1/A moves smoothly as a function of the interaction strength. So, therefore, rather than this diagram, A and R, but I think that it's better to draw 1/A and R. That is a kind of a continuous curve. And is your statement correct also in the diagram of 1/A and R?
It is actually only that the two guys now change the role. As you see here, A goes through 0. So if I plot 1/A, the compact state actually leaves the picture and come in from the other side, while here the molecule leaves the picture and comes in from the other side. But you can do it either way. If you look in this paper here, the argument is even a little more clearly presented than it is here in a very short form.
Thank you.
You're welcome.
Okay, Frank, I think you had your hand up next.
Yeah, hi, Christoph. Interesting talk. I have a comment and a question. The comment first, very nice didactics-wise prepared slide, what was it, 12 and 13 on these various bound states and virtual states. My question is a different one concerning the heterogermonium model proposed and introduced by Misha Voloshin. Does it mean that our measurement of BES3 of the Y4220 now being observed in the open charm decay excludes the heterogermonium model for the Y4260?
Well, from my point of view, this data that you see in the open charm is a clear push towards a molecular picture of, say, the Y4220 being a D1 bound state. And then probably the higher, and then part of the higher peak would even be presented by the D1D continuum, as we already have in the paper from 2014. I think really that all the different explanations for the Y4260 besides the molecular one is actually challenged by these data, simply because one needs to understand in these other pictures why the open charm decays are so strongly populated, although the phase space is tiny, versus the decay into CC bar. Well, in case of the tetraquark picture, there is some attempt of explaining that by the tunneling probability of the light quarks in such a double value being higher than the tunneling probability of the heavy quarks. And this way the authors argue, if I recall correctly in this paper here, that this actually favors the open flavor decays for the tetraquarks versus the hidden charm decays. Although I have to admit that I didn't really understand the argument. But if you want to read the details, you can find them in here.
Okay, thank you. We agree here. I mean, maybe the last question concerning that once more. I mean, in the second part of your talk, you are stressing always these fraction or amount of violation of heavy spin symmetry. But here, this is a different story. I mean, either it is a heterogermonium, then there should not be at all open charm decay, or vice versa, correct?
No, not at all. This is not the right statement. You can still have a quark rearrangement within the heterogermonium. only that the most natural and naively expected most prominent decay indeed should be the one into the compact CC bar together with the pions. Therefore, it's not excluded that these states go to the open charm, but it's difficult to explain that a certain state goes most prominently into the open charm if it is a heterocharmonium indeed. There I'm with you.
Okay.
But it's not excluded to go into the open charm.
Okay, we have one final question from Victor, please.
Thank you very much, Christoph, for excellent review of hadron physics with heavy quark. My question is, you mentioned as one of the tools to gain insight into the structure of molecule or whatever it is, you also offer other explanation, the studies of the line shape of particular resonance. My question is, in real measured spectrum of invariant mass, line shape, very complicated guy. It can come in not only from resonance, but from many other mechanisms. Any hope to get insight into the line shape? Any idea how to do this? Okay, clear.
This is what keeps us theoreticians busy. I simply did not have the time here because I wanted to also go to this double J psi spectrum, and the time was limited, and I also wanted to be fair in an overview talk to the other explanations besides the molecular case. But in the molecular scenario, we've calculated for various reactions, we've calculated all the line shapes. Say for the ZB states, you find a series of papers where we analyze the line shapes and draw non-trivial conclusions from that. But in Baru here, we'll talk about our study of the line shapes in the pentaquark spectrum. I think this talk is tomorrow, if I recall correctly, in the parallel sessions. Therefore, indeed, one can do line shape studies, but you are completely right, they are rather involved, but so are the experiments. Therefore, I think it's fair enough that you do the complicated experiments, we do the complicated theory, and at the end of the day, hopefully we all learn something.
Okay, I think those are good words to end the session. Thank you, Christoph, and I would like to thank all the speakers that we've had in this session. We're a few minutes delayed right now, so let us try to begin at 2:55. So we have a few minutes to get a cup of coffee or bio pause or whatever. So see you all back very soon.